Hello there, and welcome to Science for Sleep, where curiosity slows down, ideas stretch out, and science takes the long way around so your thoughts have room to soften as you drift toward rest. Tonight, we're setting out on a quiet exploration of something so brief, so tiny, that it almost defies imagination. We're going to talk about the shortest possible time, a moment so small that it makes a single second look like an ocean compared to a single drop. This is known as Planck time, and if you've never heard of it before, that's perfectly fine. Very few people outside physics ever need to think about something so fleeting, because it isn't about daily schedules or clocks or how late the bus is running. It's about the very foundations of the universe, the way reality itself might tick, not second by second, but in a rhythm far too fast for us to ever notice. Before we dive into that, let me ask you something simple and grounding. Where are you listening from right now, and what time is it for you? Maybe it's early morning and the day hasn't yet rushed in. Maybe it's late at night and you're lying in bed with your thoughts drifting. Maybe you've stumbled here in the middle of the day, looking for a pause, a calm corner to let your mind settle for a while. Whatever the hour is for you, think of how it feels. We live in time constantly, yet rarely do we stop to ask what time really is, let alone how small a unit of it could possibly be. If you find yourself soothed by this slow journey, or if you simply enjoy having a place where science doesn't hurry you along but walks with you gently, I'd be grateful if you liked the video or even subscribed. That way, more people who need a calm space might find it too. But don't worry about that for now. Just settle in, breathe evenly, and let's begin to unfold the question together. Because somewhere in the mathematics of the cosmos lies this strange, almost secret measure called Planck time, and it is the closest thing we have to an answer when we ask how short a moment can possibly be. The idea that time could have a minimum size might feel odd. After all, we tend to think of time as continuous, smooth, like water flowing from a tap. We can cut a second in half, then cut that half in half again, and repeat the process forever. At least that's how our intuition works. We're used to dividing things as much as we want. A cake can be sliced thinner and thinner, a distance can be broken into smaller steps, a second can be measured into milliseconds, microseconds, nanoseconds, and on and on. So why should time be any different? Why should there be a place where the slicing stops, where no smaller piece is possible? To start understanding this, it helps to look at how humans have measured time across history. We'll wander there soon enough, through sundials, water clocks, and the way we invented the second as a convenient slice of the day. But before we go there, think about your own sense of time. Have you ever been waiting for something? Maybe a phone call or for a pot of water to finally boil, and those minutes stretched unbearably long, and then, in another situation, you might spend hours with a friend or wrapped up in a book only to feel like barely any time at all has passed. That is the strange trick of perception, the way our minds bend time to our feelings. Yet beneath that elastic sense is something else, a world of measurement and physical limits, where science asks not how time feels, but what it is made of and whether there is an ultimate boundary. The smallest slice of time known in physics, Planck time, was not discovered in the way we discovered seconds or minutes. Nobody built a clock and saw it tick that fast. Instead, it emerged from the effort to stitch together different parts of physics, the parts that describe gravity, motion, and the quantum world. It's not that we have a stopwatch capable of measuring it. It's that our equations suggest that below this unimaginably brief instant, the very idea of time starts to lose meaning. Imagine numbers so extreme that they almost stop being numbers and instead become a kind of limit, like the edge of a map where there is no further territory drawn. That's what Planck time is. Not a measured beat, but a threshold suggested by the language of mathematics. To give a sense of scale, let's recall that a single second can be split into 1,000 milliseconds. A blink of the eye takes perhaps 200 or 300 of those. Now shrink a millisecond further into 1,000,000 microseconds, then keep shrinking into nanoseconds, the scale of electronics, and then into femtoseconds, the scale of chemical reactions. Already you're far below anything you can notice with your senses. A nanosecond is to a second as a second is to 30 years. And yet physics goes smaller still, far smaller. When we arrive at Planck time, we're talking about a number so small it defies everyday comparison. It is about 10 to the negative 43 seconds. Written out, that's a decimal point followed by 43 zeros and then a 1. No blink, no beat, no flicker of thought comes close to this interval. You might ask, what does it mean to say something takes that long, if no event in daily life could ever be measured so precisely? The answer lies in theory. The Planck time is defined through fundamental constants of nature, the speed of light, the gravitational constant, and Planck's constant, which describes the granularity of the quantum world. Put them together in just the right way, and the result is a time interval, the Planck time, which physicists suspect is the shortest meaningful tick of the universe's clock. Anything shorter may simply not exist as a separate moment, because the physics we know cannot describe it. Now this might sound abstract, and in many ways it is, but think of it this way. When you zoom in on a photograph enough, you eventually stop seeing shapes and instead see pixels. Planck time is like the pixel size of the timeline. It tells us that the universe may not flow smoothly forever into smaller and smaller divisions, but instead has a granularity, a smallest step, beyond which time itself loses definition. And this is where our quiet exploration will carry us tonight. From the way people first slice the day into hours, to the invention of the second, and then to the quantum foundations that reveal a boundary so small it strains the imagination. Along the way, we'll ask why physics stops at Planck time, what it might mean for the earliest moments of the universe, and whether this smallest tick is real or only a mathematical tool. But we won't rush. Each part of the story will stretch out gently, giving you space to let the ideas wander in your mind. Because if there's anything more astonishing than the vastness of time, it is the idea that time itself might have a flaw, a place where the slicing finally stops. When we say the phrase, the shortest time, it can sound deceptively simple. After all, we're used to talking about short times every day. A few minutes before dinner is ready, a couple of seconds to send a message, maybe a fraction of a second for a sprinter to react to the sound of the starting pistol. In daily life, we constantly deal with small intervals of time, and they don't seem particularly mysterious. But when scientists ask about the shortest possible time, they mean something far more fundamental. They're not asking how quickly a person can blink, or how long a computer chip takes to carry out an instruction. They're asking whether the fabric of the universe itself allows time to be divided endlessly, or if there's a smallest possible slice, a point beyond which time can no longer be chopped into smaller pieces. This question immediately takes us into a strange and slippery world, because our ordinary intuition about time doesn't give us much help. If you look at a clock, the hands sweep smoothly. If you check your phone, the numbers change in neat increments. If you listen to your heartbeat, it thuds in a rhythm you can feel. All of these examples suggest that time just flows, steadily and without interruption. And if something flows, surely you can divide it as much as you like. Just as you can take a stick and cut it in half, then cut one of the halves in half again, and repeat that without end, it seems natural to assume that you can keep cutting time into smaller and smaller fractions forever. But physics has a way of interrupting our assumptions. In many areas of science, when researchers have looked for ultimate limits, they've sometimes discovered that nature doesn't go on forever in the way we expect. For instance, you might think that you can keep dividing matter into smaller parts indefinitely. For centuries, people believed that matter was continuous, that you could always break it down further. Eventually, scientists discovered atoms, and then inside atoms, particles like protons and electrons, and then inside those, quarks. As far as we know, quarks can't be split any further. there's a point where the slicing stops. Something similar happened with light. To the human eye, light looks like a smooth glow. For a long time, it was treated purely as a wave. But in the early 20th century, scientists realized that light comes in discrete packets called photons. It isn't continuous after all. It's quantized, made of fundamental pieces. So the question arises, could time also be like this? Could time itself be quantized, broken into indivisible units, where no smaller subdivision is possible? That is what physicists are getting at when they ask about the shortest time. They're not asking about practical limits of clocks or the patience of people waiting in line. They're asking if the very structure of the cosmos has a built-in minimum tick, the smallest possible moment before the idea of moments loses meaning. To start approaching that question, it helps to think about how we define time in the first place. Most of us don't stop to consider this, but time is always measured indirectly. We never measure time itself. Instead, we measure change. A pendulum swings, a planet orbits, an atom vibrates. Each of these repeating processes can be used as a reference. We say one swing takes this long, or one orbit takes a year, or so many vibrations equal a second. Without change, there would be no way to count time at all. If the universe were frozen in place, no movement, no oscillations, no ticking, there would be no way to mark a before and an after. In that sense, time is inseparable from events. It's always about how things unfold. The modern definition of a second is based on the vibrations of a cesium atom. Specifically, 1 second is defined as 9,192,631,770 oscillations of the radiation, corresponding to the transition between two energy levels of cesium-133. That number may seem arbitrary, but it gives us a precise standard. With this, atomic clocks can measure time to astonishing accuracy. But even though this definition works incredibly well for daily life, it's still a human choice, a way of anchoring our measurements to a reliable process. It doesn't answer the deeper question of whether time itself has a smallest scale. It's like agreeing on a ruler to measure wood, but not knowing if the wood itself is made of tiny grains that limit how fine your cuts can get. The search for the shortest time leads us into the meeting place between two of the great theories of physics. On one side, we have quantum mechanics, which describes the very small, the world of particles and probabilities. On the other side, we have general relativity, which describes the very large, the fabric of space-time and the pull of gravity. Each of these theories works beautifully in its own realm. But when scientists try to use them together, things start to break down. At extremely small scales, where quantum effects and gravity both matter, our equations don't quite cooperate. This is the territory where Planck time enters the story. Planck time is defined by combining three fundamental constants of nature: the speed of light, which tells us how fast information and energy can move, the gravitational constant, which sets the strength of gravity, and Planck's constant, which governs the quantum graininess of energy. When you put these together, you arrive at a number, about 539 times 10 to the negative 44 seconds. This is the Planck time. To get a sense of how small this is, imagine dividing 1 second into a trillion parts. That gives you a picosecond, already too small to notice in daily life. Now divide again and again, trillions of times over. The Planck time is smaller than anything in that cascade, smaller than anything your imagination can comfortably hold. Why does this number matter? Because it seems to mark a boundary. Below this interval, our current understanding of physics stops working. If you try to describe events happening in a span shorter than the Planck time, the equations of relativity and quantum mechanics no longer make sense together. It's as if nature is telling us that time cannot be chopped more finely than this. It's not that we can't measure smaller intervals, though that's certainly true in practice. It's that the concept of smaller intervals may not exist in reality. The very idea of before and after loses its meaning at that level. This is why physicists say the Planck time is the shortest possible time. It's not about a clock we could ever build. It's about a limit built into the structure of the universe. Just as you can't travel faster than light, you may not be able to experience or describe time in steps smaller than the Planck time. It's a fundamental flaw below which the universe's usual rules collapse into uncertainty. When we ask what we mean by the shortest time, then we're really asking whether time is continuous or discrete, infinite or finite in its divisions. It's the same kind of question people asked about matter or light, only applied to the most universal backdrop of our lives. If the answer is that time has a smallest unit, then reality itself is built on tiny indivisible moments, strung together like frames in a film. If the answer is that time is continuous, then in principle you could keep dividing it forever. The existence of Planck time suggests the first option, that time has an ultimate granularity, though this remains a subject of deep investigation. Another way to understand this is to think about what happens in the very early universe. According to cosmology, the universe began about 13.8 billion years ago in what we call the Big Bang. But if you rewind all the way back, the first 10 to the negative 43 seconds, roughly one Planck time after the beginning, lies in a domain where our laws of physics cannot describe what happened. This is sometimes called the Planck era. Before that time, or at timescales smaller than that, we simply don't know what the universe was like, because our equations lose their grip. That's how central Planck time is. It's not just an abstract number, it's a boundary in our knowledge, a horizon beyond which we can't yet see. It's worth pausing here to reflect on how strange it is that such a limit exists. Think of all the things you do in a second. Your heart beats, your eyes blink, your brain fires countless neurons. All of this happens on scales of milliseconds to fractions of seconds. Technology has pushed deeper, measuring nanoseconds in electronics and femtoseconds in laser pulses. Yet physics says there is a bottom, a point so far below any of that that we can't even imagine an experiment to probe it. That is what makes the question of the shortest time so fascinating. It's not about human experience anymore. It's about the ultimate architecture of reality. And so, when scientists talk about the shortest time, they're not referring to what we can perceive or even what we can measure with our best instruments. They're referring to a theoretical limit, an interval so brief that it anchors the very notion of time itself. It is the point where our two greatest theories collide, and where new physics, still undiscovered, must eventually take over. This is why Planck time is more than a number. It's a clue, a signpost that tells us there's something deeper to uncover about how the universe works. When we wonder about the shortest time possible, it's easy to get lost in the abstract numbers of modern physics. But before we had equations filled with constants and concepts like Planck time, human beings were simply trying to make sense of their days and nights. Long before atomic clocks and satellites, before pendulums and gears, people needed some way to measure the passage of time. Not the kind of deep cosmic questions about beginnings and boundaries, but practical needs: when to plant crops, when to gather for rituals, when to begin or end work, when to expect the flooding of a river or the return of the seasons. The story of timekeeping begins here, in the lives of people who looked at the natural world to find patterns they could rely on. If you think about it, the first way humans sliced time wasn't with tools at all. It was with the sky. The rising and setting of the sun, the phases of the moon, the yearly swing of the stars overhead. These were the earliest clocks. You didn't need numbers to know when dawn had broken, or when the full moon would appear, or when winter was approaching. Life was structured by these enormous reliable cycles. A day began when the sun returned, and ended when darkness settled in. A month was marked by the waxing and waning of the moon. A year was known by the tilt of the sun's path and the turning of the seasons. For early humans, this was enough. The cycles of nature told them when to hunt, when to move, when to rest. But humans are restless creatures, always searching for ways to divide, measure, and organize. It wasn't long before they began trying to carve the day itself into smaller pieces. The ancient Egyptians were among the first to develop formal methods for tracking time. Around 3,500 years ago, they used tall stone obelisks that cast long shadows in the sun. By watching how the shadow shifted through the day, they could mark the passage of hours, though those hours weren't yet the equal units we think of today. In summer, when the days were long, each hour was longer. In winter, when daylight was short, each hour was shorter. Hours were not fixed, but tied to the changing length of the day. Still, it was a step toward dividing time into smaller slices, a way of looking beyond the simple rise and fall of the sun. Sundials soon followed, more portable than massive obelisks, but based on the same principle. A stick planted in the ground, or a carefully crafted stone with markings, could tell you the approximate time by the angle of its shadow. Sundials spread widely across ancient civilizations, from Egypt to Greece to China. They were useful, but they had an obvious limitation. No sun, no time. Cloudy days or nights left them useless. People began searching for other ways to track hours when the sky was hidden. That search led to water clocks, known as clepsydras. These were used in Egypt, Greece, China, and beyond. The simplest version was just a vessel with a small hole at the bottom, allowing water to drip out steadily. By marking the level of water inside, you could tell how much time had passed. More elaborate versions had floating figures or gears that would move as the water flowed, even striking bells to mark the hours. These devices could work at night, making them more versatile than sundials, but they were still imprecise, influenced by the temperature and pressure of the water. Even so, they showed an important shift. Humans were no longer just observing natural cycles. They were building artificial tools to impose their own order on time. In Mesopotamia, the Babylonians and Sumerians also made important contributions. They divided both the day and the circle into units of 60. That's why we have 60 seconds in a minute and 60 minutes in an hour today. Their base 60 system may seem unusual now, but it was very practical for dividing things into equal parts, since 60 has many divisors. This mathematical choice, made thousands of years ago, still shapes every clock we look at today. In China, water clocks became incredibly sophisticated, with complex mechanisms that allowed them to be calibrated more accurately. By the first millennium, they had developed astronomical water clocks that tracked not only the hours, but also the movements of celestial bodies. These were monumental machines, blending engineering with cosmology, showing how closely timekeeping was tied to the observation of the heavens. In the Americas, civilizations like the Maya developed remarkably precise calendars based on both solar and lunar cycles. Their calendars could predict eclipses and track vast cycles of time stretching thousands of years. For them, timekeeping wasn't only practical, it was spiritual, woven into their understanding of the cosmos and human destiny. Time wasn't just divided for farming or trade, it was a sacred rhythm, and to follow it was to align with the universe itself. Looking at all these early efforts, you can see a pattern. The first slicing of time wasn't about seconds or milliseconds, it was about carving the day into usable chunks, aligning human life with natural cycles, and then slowly pushing further towards smaller and smaller divisions. Each step forward reflected both a need and a curiosity. People needed to organize, to meet at the right time, to plant at the right season. But they also seemed to have a natural urge to divide the flow of life into ever finer segments, to capture something that constantly slips away. Imagine yourself in an ancient village thousands of years ago. There are no clocks, no alarms, no phones to remind you of the hour. You rise with the sun because the light wakes you. You rest when darkness makes work impossible. If you need to meet someone, you say, when the sun is halfway or when the shadow is long. Time is measured by observation and experience, not by numbers on a dial. But then someone places a stick in the ground and notices how its shadow shifts predictably. Suddenly, you have a way to be more precise. You can say, "We will meet when the shadow reaches this mark." And just like that, human life gains a new layer of structure. From there, the drive to improve never really stopped. As societies grew more complex, so did their need for more exact time. Markets, ceremonies, travel, governance, all required coordination. Timekeeping wasn't just a curiosity, it became a foundation for social order. Without some shared sense of time, large groups of people couldn't work together effectively. That pressure to synchronize lives kept pushing the slicing of time into smaller and smaller pieces. It's important to notice how deeply cultural these early methods were. In some places, hours weren't fixed but stretched and shrank with the seasons. In others, time was tied to cycles of ritual and religion rather than uniform measurement. Some languages don't even treat time as a linear thing, but as a landscape or a set of conditions. The way we think of hours and minutes today isn't universal. It's the result of specific choices, inventions, and agreements built layer by layer over millennia. When we reflect on how humans first sliced time, it highlights just how recent our obsession with precision really is. For most of history, people didn't need to know what minute it was. The difference between late morning and early afternoon was more than enough. The idea of measuring a second, let alone anything smaller, would have seemed strange, even unnecessary. And yet, the seeds of that journey were already planted in those first sundials and water clocks. Once you start dividing the day into parts, once you start asking how much time has passed between one event and another, you set yourself on the road toward ever finer measurements. What's striking is how this story reflects the larger theme of Planck time. Just as early people asked, how can we divide the day, and kept slicing it thinner and thinner, we now ask, how far down can time itself be divided? Each generation pushes the boundary, and each discovery reveals both new possibilities and new limits. The journey from obelisks casting shadows to atomic clocks measuring vibrations is the same journey that eventually brings us to the strange limit of Planck time. The curiosity is the same. The scale is what has changed. And so, as we think about how humans first sliced time, we can see not just an ancient story, but the beginning of a path that still continues. From watching the sun rise, to counting the drips of water, to tracking the cycles of the moon, people learned to capture time in manageable portions. Each tool they built was a little more precise, a little more ambitious. They probably didn't imagine that someday scientists would ask about 10 to the negative 44 seconds. But the impulse that started it all was already there. The need to divide, to count, to measure, to make sense of the flowing moments of life. When people first learned to divide the day using shadows, water, or the movement of the moon, the slices they created were still very large. The hour, as it first existed, was not the neat 60-minute package we think of today, but a rough measure that varied with the seasons. Life in those early centuries didn't demand more precision than that. For farmers and builders, for priests keeping track of rituals, it was enough to know when the sun was halfway across the sky, or when a water clock had emptied a vessel. But slowly over time, societies grew in complexity. Trade routes spread across regions. Armies had to march in step. Cities required organization. Religion, too, often required that prayers or rituals be carried out at specific intervals. These needs pushed humans to ask for smaller slices, more reliable divisions, and systems that could be shared across distances. The sundial, for all its usefulness, could only go so far. It worked well under clear skies, but not at night, not in cloudy weather, and not indoors. Water clocks provided some improvement, but they too were imperfect. Their rate could change with temperature or the size of the outlet hole. Even so, both sundials and water clocks began to teach people to think of time in smaller increments. Once you're used to hours, you start to wonder about halves of hours, then quarters, and eventually minutes. The story of minutes and seconds is deeply tied to the mathematical systems of the Babylonians. They used a base 60, or sexagesimal system for mathematics. Unlike our modern base 10, which revolves around the number 10, their system divided things by 60. This choice wasn't arbitrary. 60 can be divided evenly by many numbers: 2, 3, 4, 5, 6, 10, 12, 15, 20, and a 30. That made it extremely practical for splitting up circles, angles, and eventually hours. From this system, we inherited the division of a circle into 360 degrees, and importantly for our story, the division of an hour into 60 minutes, and each minute into 60 seconds. The echoes of a decision made in Mesopotamia more than 4,000 years ago still ring through every digital display we look at today. But although the framework of minutes and seconds was established mathematically, the tools to measure them accurately took centuries to arrive. For a very long time, minutes and seconds were theoretical units, not ones that daily life could actually track. Water clocks could approximate them, but they were too inconsistent to give everyone the same reading. It wasn't until mechanical clocks emerged in medieval Europe that these smaller slices began to take on practical meaning. The earliest mechanical clocks appeared in monasteries around the 13th century. Their primary purpose wasn't for daily commerce or appointments, but for regulating prayer. Monastic communities followed strict schedules with prayers at regular intervals throughout the day and night. To keep these rituals consistent, they needed clocks that could chime the hours reliably, regardless of whether the sun was visible. These early clocks were enormous machines, often installed in towers, and their dials, when they existed at all, were simple compared to what we know today. They often lacked minute hands entirely. Time was still counted in hours, not finer divisions. But the march towards smaller units was relentless. By the 14th century, clockmakers developed mechanisms like the verge escapement, which allowed mechanical clocks to regulate the release of energy more steadily. With these advances, it became possible to display not only hours but also minutes. By the 16th century, clocks with minute hands were appearing, though they were still far from precise by modern standards. A clock might drift by several minutes each day, but for people at the time, that was already revolutionary. The second, though defined mathematically, remained elusive in practice. It was too small a unit for everyday life, and no clock was yet accurate enough to measure it meaningfully. Still, the idea of the second lingered, tied to the Babylonian inheritance of 60 divisions within a minute. People could write it, calculate with it, and imagine it, even if they couldn't yet track it in real life. The desire for greater precision was not going away. As navigation, astronomy, and science advanced, so too did the demand for smaller and smaller slices of time. Astronomy played a particularly important role in shrinking time. Observing the heavens required tracking very slow, gradual motions across the sky. Small errors in timekeeping could lead to large errors in predictions. For sailors, accurate time was more than academic. To determine longitude at sea, navigators needed to know the precise time back at a reference point, such as Greenwich, while comparing it to local observations of the sun. Without accurate time, ships could drift hundreds of kilometers off course, with potentially disastrous results. This pressure to measure smaller slices of time accurately and consistently fueled enormous efforts in clockmaking. By the 17th century, pendulum clocks arrived, thanks to Christian Huygens, a Dutch scientist and mathematician. The pendulum provided a steady, reliable swing, and suddenly, clocks could be accurate to within a minute a day, a staggering improvement over earlier designs. With pendulum clocks, minutes became far more practical, and seconds finally began to step into daily use. Some pendulum clocks even included a second hand, making the theoretical unit of ancient mathematics a living, ticking measure in the present. This was a turning point. For the first time in history, ordinary people could look at a clock and see the seconds counted out before their eyes. The shrinking of time's units was no longer just about scholars or astronomers. It was entering the rhythm of everyday life. By the 18th and 19th centuries, as industrial society expanded, seconds became ever more important. Factories required precise coordination. Railroads demanded strict schedules. Telegraph signals needed synchronized timing. Time was no longer just about sunrise and sunset, or the sounding of bells in a monastery. it became a shared standard across entire nations and then across the globe. It is almost strange to think how recent this development really is. For most of human history, nobody needed to know what second it was. Even the idea of minutes would have been excessive for a farmer planting crops or a shepherd tending animals. But once technology, commerce, and science demanded more precision, the clock adapted, and the units we still use today, hours, minutes, and seconds, became part of the fabric of daily life. The shrinking of time into seconds also changed how people thought about their own lives. Before, you might measure the span of a task in hours, or simply in until sunset. Now, with seconds visible on a dial, time became something sharper, something you could count in exact beats. That shift helped shape modern culture, with its constant attention to punctuality, deadlines, and schedules. The slicing of time into smaller and smaller pieces didn't just help sailors navigate oceans or astronomers chart the stars. It changed how ordinary people experienced the flow of their days, and still, even as seconds became part of our lives, the desire for smaller slices continued. In the 19th and 20th centuries, as physics and technology advanced, scientists began talking about milliseconds, microseconds, nanoseconds. Each step smaller revealed new worlds, the timing of electrical circuits, the vibrations of molecules, the oscillations of atoms. Each step opened new doors in both science and industry. But the foundation for all of this was laid when we moved from sundials casting shadows to the invention of hours, then minutes, and finally, the second. When we look back at that journey, it becomes clear that humans have always carried the same impulse. From ancient obelisks to digital watches, from dripping water to atomic vibrations, the story has always been about slicing time thinner, chasing precision, and trying to capture something that constantly slips away. Each tool we built gave us a smaller unit. Each smaller unit gave us more control, and each gain in control opened new possibilities. That journey doesn't stop at the second. It goes all the way down to the smallest slices our theories will allow. And so, the shrinking of units from sundials to seconds is more than a story about technology. It's a story about curiosity and necessity intertwining. People didn't set out to measure nanoseconds when they first watched the shadow of a stick move across the ground. They simply wanted to organize their days. But each step forward created new needs and new possibilities, until eventually the march of smaller and smaller divisions brought us face to face with something extraordinary. The idea that there might be a fundamental limit, the Planck time, beneath which no smaller slice of time can exist. As minutes and seconds gradually entered daily life, something subtle began to happen. These units stopped being just convenient slices of the day and started to take on the role of universal standards. At first, the second was little more than a mathematical inheritance, tucked away in Babylonian arithmetic and whispered into mechanical clocks centuries later. But over time, it transformed into something far more fundamental, the base unit upon which the modern world rests. The journey toward the scientific second is, in many ways, the story of how humanity learned not only to divide time, but to agree on what that division meant, to refine it so carefully that the smallest inconsistencies could be noticed, and to anchor it in nature itself rather than in the shifting rhythms of the sun or the imperfections of machines. In the earliest days, when clocks were still large, clanging machines in monasteries and town squares, there was little agreement between regions about how long a second truly was. Hours themselves could stretch and shrink depending on latitude, season, and tradition. Even as mechanical clocks improved, they were only as reliable as the craftsmanship behind them, and drift was common. For most people, this was not a crisis. If a clock gained or lost several minutes in a day, it was irritating, but it did not upend the functioning of a community. But for science, navigation, and increasingly for trade, this looseness was a problem. When your task is predicting the orbit of a planet, plotting the course of a ship across the ocean, or synchronizing activities across cities, minutes matter, seconds matter. A reliable and universally agreed upon measure of time was becoming a necessity. Astronomy provided the first anchor. For centuries, time was defined by the rotation of the Earth. A day was the time it took for the planet to spin once on its axis, and all other units were subdivisions of that. Hours, minutes, and seconds were carved from the day itself, like cutting a loaf into smaller slices. In this system, a second was defined as 1/86,400th of a mean solar day, since there are 24 hours in a day, 60 minutes in each hour, and 60 seconds in each minute. This seemed straightforward enough. As long as the Earth continued to turn, the day provided a dependable backdrop. But the closer scientists looked, the less dependable it seemed. The Earth does not rotate with perfect consistency. It wobbles, it slows down slightly over centuries, it is tugged by the moon and influenced by shifts in its own mass. Earthquakes, melting glaciers, the motion of the core, all of these can subtly alter the length of a day. To a farmer in antiquity, these changes were invisible. To a physicist or navigator relying on precision, they introduced unavoidable uncertainty. It became clear that if the second was tied directly to the Earth's rotation, then it would never be perfectly stable. That realization set humanity on the path to defining time in terms that were deeper than the motions of the planet beneath our feet. The transition didn't happen overnight. For a long while, astronomical observations were refined and improved, with more accurate telescopes and methods for tracking the stars. The concept of mean solar time was developed, averaging out the irregularities of Earth's rotation over long periods. This gave a more consistent framework, but the seeds of dissatisfaction had been planted. The hunt was on for a way to define the second that would not drift with the planet's imperfections. By the late 19th and early 20th centuries, scientists began to look beyond Earth altogether. The orbital mechanics of the solar system offered a possible solution. Instead of defining the second by the Earth's spin, why not define it by its orbit around the Sun? A year is the time it takes for Earth to complete one orbit, and a second could be defined as a tiny fraction of that. This idea led to the concept of ephemeris time. Introduced in the mid-20th century, ephemeris time was based on the orbital motion of the Earth around the Sun as calculated from Newtonian mechanics and astronomical observations. It was more stable than the Earth's rotation, and for a while it provided a better anchor. But even ephemeris time required constant recalibration and was tied to measurements that were complicated and not easily reproduced in laboratories around the world. The real breakthrough came when scientists turned their gaze inward, to the quantum world. Instead of anchoring the second to astronomical events, they asked if it could be tied to something much more fundamental, the behavior of atoms. Atoms, after all, are the building blocks of matter, and their properties are the same everywhere in the universe. If time could be measured by the vibrations or transitions of atoms, then the second could finally become universal, freed from the quirks of planets and orbits. This is where cesium-133 enters the story. In 1967, the General Conference on Weights and Measures adopted a new definition of the second. From that point onward, 1 second was defined as exactly 9,192,631,770 cycles of the radiation associated with the transition between two hyperfine energy levels of the ground state of the cesium-133 atom. That long string of numbers may sound oddly specific, but it represented a triumph of precision. Atomic clocks based on cesium could keep time with an accuracy that left all previous methods in the dust. No drift from wobbly Earth rotations, no dependence on orbital mechanics, just the steady, universal rhythm of atoms, available to any laboratory with the right equipment. With this change, the second became truly scientific, rooted not in local circumstances, but in the very constants of nature. The journey that began with sundials and water clocks had finally reached the atomic scale. From then on, atomic clocks would define not just seconds, but the synchronization of entire systems, global navigation satellites, telecommunications networks, scientific experiments, financial systems. Our entire modern infrastructure now leans on the definition of the second set by cesium atoms. But the story doesn't end there. Even cesium clocks, as remarkable as they are, have limits. Over time, physicists have developed even more precise atomic clocks using other atoms and techniques, such as optical lattice clocks that rely on strontium atoms. These clocks can be so precise that they would not gain or lose a second over the entire age of the universe. The pursuit of ever finer precision continues, because with each step new scientific possibilities open. Measuring time more accurately allows us to test fundamental physics, to refine our understanding of relativity, to synchronize systems across the globe, and to probe questions at the edge of cosmology. It's remarkable to think that the unit we now take for granted, the second, has such a long and winding history. From being an abstract mathematical division, to being a rough slice of a day, to being tied to the spin of the Earth, to being redefined by its orbit around the Sun, and finally to being anchored in the vibrations of atoms, the second has undergone a journey that mirrors our growing understanding of the universe. Each step represented a demand for greater accuracy, driven by needs that range from farming to navigation to the deepest questions of science. When we think about Planck time, that ultimate smallest slice of time our physics allows, it's worth remembering that it sits atop this long ladder. Without sundials and water clocks, without pendulums and ephemeris time, without the cesium standard, we wouldn't even have the language or tools to talk about something as abstract as the Planck scale. Each refinement brought us closer, each step downward into smaller units made us more comfortable with the idea that time is something that can be sliced again and again. The scientific second is more than just a practical tool. It's a symbol of our determination to find stability and universality in a universe that often seems chaotic and shifting. Anchoring time to the behavior of atoms was a way of saying, this measure belongs not to one culture, one region, or one planet, but to the cosmos itself. Any observer anywhere in the universe who understands cesium could, in principle, reproduce the same second. That universality makes the second not just a unit of time, but a bridge between humanity and the universe. From here, the story naturally drifts toward the limits of precision, because once you have defined time with such rigor, it raises the next question. How much further can you go? How small a slice can you measure? What happens when your equation suggests that there is a boundary, a point beyond which no smaller unit of time makes sense? When the second was finally anchored not to the Earth's irregular spin or the long sweep of its orbit but to the steady rhythm of atoms, humanity entered a new era. It was a shift that might sound subtle, even invisible to most people going about their daily lives, but in truth, it transformed the very foundations of how we measure and understand time. This was the age of atoms, when time stopped depending on the movements of celestial bodies and instead began ticking to the tune of nature's smallest building blocks. At the centre of this story sits a quiet, unassuming element: cesium. Cesium is not a household word, though it occasionally surfaces in discussions of chemistry or electronics. It is a silvery gold metal, soft and reactive, one of the alkali metals that sits near potassium and sodium on the periodic table. In its pure form it will melt in your hand, though you wouldn't want to touch it, since it reacts violently with water. Yet beneath its shimmering surface, cesium has a gift. Its atoms vibrate with remarkable stability. In particular, cesium-133, one isotope of the element, has a property that makes it a perfect metronome for defining time. The story of how cesium came to define the second begins with a simple problem. As precise as pendulum clocks were, as advanced as astronomical observations had become, the world was demanding more. By the middle of the 20th century, technologies such as radio communication, global navigation, and increasingly sophisticated scientific research required timing that was more stable and more universal than anything tied to the Earth's motion. The irregular wobble of the planet was no longer acceptable as a time standard. Scientists wanted something that would not drift with earthquakes, atmospheric changes, or the slow tidal drag of the moon. They wanted something absolute, something that would be the same for anyone, anywhere, regardless of circumstance. Atoms offered that possibility. The idea was that if time could be defined by the transitions within atoms, then it would no longer depend on external factors. An atom, isolated and undisturbed, is the same in Paris as it is in Tokyo, the same on Earth as it would be on Mars, or in some distant laboratory orbiting another star. The hope was that nature itself could provide the universal standard humans had been searching for. Cesium-133 turned out to be the ideal candidate. Atoms have energy levels, and electrons within those atoms can shift between levels when they absorb or emit precise amounts of energy. These shifts are not random. They're governed by the fundamental laws of quantum mechanics. In cesium-133, one of the most useful transitions occurs between two hyperfine levels of its ground state. The radiation emitted or absorbed during this transition oscillates at an extraordinarily steady rate. Count those oscillations and you have a natural clock, one that ticks far more consistently than any pendulum or mechanical gear ever could. In 1955, the first practical cesium atomic clock was built in the United Kingdom by Louis Essen and Jack Parry at the National Physical Laboratory. This machine looked nothing like the clocks we're familiar with in homes or on wrists. It was a bulky device filled with electronics, vacuum chambers, and carefully controlled conditions. But it achieved something remarkable. It kept time with unprecedented precision. By the 1960s, atomic clocks based on cesium were being adopted worldwide as the most accurate timekeepers ever created. In 1967, the scientific community made a historic decision. At the General Conference on Weights and Measures, the definition of the second was officially redefined in terms of cesium. No longer was a second tied to Earth's rotation or orbit. From that moment on, a second was defined as exactly 9,192,731,770 oscillations of the radiation corresponding to the transition between the two hyperfine levels of the ground state of cesium-133. That long string of digits is not just a technical detail, it is the heartbeat of modern civilization, the rhythm by which everything from satellites to stock markets keeps time. This definition was revolutionary. By choosing cesium, scientists had effectively declared that time itself should be measured by a process that was not only precise, but also universal. Any laboratory with the right equipment could reproduce the second anywhere in the world, and it would match perfectly with every other laboratory. In principle, even an alien civilization with a knowledge of quantum mechanics could reproduce it. The second was no longer a human convenience. It had become a fundamental slice of reality, defined by the universe itself. The practical implications of this shift were profound. With cesium clocks, timing could be accurate to within billionths of a second. That may sound almost absurdly fine, but it made possible technologies we now take for granted. Consider the Global Positioning System, GPS. Satellites orbiting Earth use atomic clocks to synchronize signals. By comparing the arrival times of these signals, your phone can calculate your position on the planet to within a few meters. Without the precision of cesium-based seconds, GPS would simply not work. Telecommunications, too, rely on synchronized timing to transmit signals around the globe. Financial systems, scientific experiments, space exploration all depend on the consistency of atomic clocks. It is striking how something so arcane, the vibration of an electron within cesium, touches so much of modern life. Every time you check a map on your phone, every time you stream a video across the world, you're leaning on cesium atoms humming away in satellites and laboratories. The smallest beat of the atomic world has become the foundation for the sprawling complexity of global civilization. And yet, the cesium clock is not just a tool. It is also a window into the nature of time itself. Because atomic clocks are so precise, they allow us to test the predictions of physics in ways that would otherwise be impossible. For example, Einstein's theory of relativity tells us that time flows differently depending on speed and gravity. Atomic clocks have confirmed this. Place two cesium clocks at different altitudes, and the one closer to the ground, where gravity is stronger, will tick more slowly than the one higher up. The difference is tiny but measurable. Time is not absolute, and cesium clocks have shown us that with stunning clarity. This makes the age of atoms not only a story of technology, but also a story of discovery. By defining time with cesium, we gained a standard that could reveal the subtle warping of time predicted by relativity, the tiny shifts that remind us that time is not just a neutral background, but something woven into the structure of space itself. Every advance in atomic clocks brings new possibilities for exploring physics at the deepest levels. Even today, scientists continue to push beyond cesium, experimenting with optical lattice clocks that use strontium or ytterbium atoms. These new devices can be hundreds of times more precise than cesium, able to detect the difference in time between your head and your feet simply because of the change in gravitational potential. But the era of cesium remains foundational. It was the first moment when humanity said, "We will no longer let Earth's irregularities define time. We will let the universe's atoms set the beat." If we step back, it is almost poetic, though not in the sense of verses or rhythm, but in the way a quiet truth resonates. The flow of time that governs our days is ultimately tied to the tiniest shifts inside a single type of atom, something that most of us will never see or touch directly, something that reacts dangerously with water and melts almost like butter, has become the cornerstone of our schedules, our science, and our sense of order. From the ancient shadows of sundials to the invisible oscillations of cesium, the journey reveals just how far humans will go to tame the intangible. But this pursuit also brings us closer to the question we began with. If cesium can define the second so precisely, if atomic clocks can slice time into billionths of seconds, what happens when we keep asking for smaller and smaller divisions? At what point does the slicing stop? Atomic definitions brought us stability, but they also pointed us toward the next frontier, because once you've reached billionths of a second, it is natural to wonder about trillionths, quadrillionths, and beyond, until eventually you run into the theoretical boundary of Planck time. The age of atoms, as remarkable as it is just one more step on the path toward the ultimate question: what is the shortest possible time? When cesium became the standard for defining time, it seemed as though humanity had finally found something absolute, a measure that was steady, universal, and reliable enough to underpin the workings of the modern world. But the very success of atomic timekeeping carried with it a deeper question. If cesium can divide the second into billions of oscillations, if new atomic clocks can refine this even further, how far can the process go? Is time something we can slice endlessly, peeling away layer after layer into ever smaller fragments? Or is there a point where the act of dividing breaks down, where nature itself draws a line? This is the search for the fundamental limit, the point at which the pursuit of precision stops, not because our tools fail, but because reality has nothing smaller to give. It is worth pausing to notice what precision really means in this context. To an ordinary person, a second feels short enough. Blink your eyes and a second has passed. Count 1 Mississippi and you have measured roughly the same. With cesium clocks, however, a second is no longer something vague. It is pinned down to over 9 billion vibrations of an atom, each oscillation as steady as the tick of the most perfect metronome. For scientists, this turns time into something granular, something that can be counted out in discrete steps. The journey of measurement no longer stops at seconds. It plunges into milliseconds, microseconds, nanoseconds, and beyond, each name marking another 1,000-fold decrease in scale. Once cesium was established as the standard, it did not take long for physicists to begin pushing further. They asked whether other atoms could serve as even better clocks. strontium, ytterbium, aluminum, all offered transitions that could be probed with lasers at optical frequencies, oscillating much faster than the microwave radiation of cesium. These so-called optical lattice clocks can divide a second into quadrillions of ticks, opening the door to a level of precision that makes cesium, for all its importance, seem almost crude by comparison. Some of these devices are so stable that they would not lose or gain a second over the entire age of the universe. With instruments like this, scientists can measure time in ways that reveal subtleties invisible to anything less precise. These advances have practical value, of course, for technologies like navigation, communication, and even geology, where atomic clocks can detect minuscule changes in gravitational potential by comparing how time passes at different altitudes. But beyond the applications, there is a deeper drive. Each improvement in precision allows physicists to test the foundations of reality itself. Relativity, for example, tells us that time is not the same for all observers. A faster moving clock ticks differently than one at rest. A clock near a massive object ticks more slowly than one far away. With ordinary timekeeping, these effects are invisible. With atomic clocks that count quadrillions of oscillations, they become undeniable, measurable in the span of minutes or hours. The pursuit of precision becomes a way of probing the very fabric of space and time. And yet, as precise as these clocks are, they still leave a lingering question. Can this refinement continue forever? Can we keep slicing time into femtoseconds, attoseconds, zeptoseconds, and even smaller? In a sense, we already have. Modern experiments with ultra-fast lasers can probe chemical reactions that occur in femtoseconds, a millionth of a billionth of a second. Physicists have measured events lasting just a handful of attoseconds, revealing the movement of electrons within atoms. In 2020, researchers reported measuring the time it takes for a photon to cross a hydrogen molecule, around 247 zeptoseconds, or a trillionth of a billionth of a second. Each step downward is an achievement, each one a demonstration that time can be sliced thinner than anyone once imagined. But beneath this extraordinary progress lies an uneasy realization. If we can always go smaller, where does it end? Does time itself have an ultimate pixel, a smallest possible unit beyond which it cannot be divided? Or is it continuous, flowing smoothly no matter how closely you zoom in? This is the heart of the search for the fundamental limit. Physics suggests that such a limit does exist, and it has a name: Planck time. Defined as the time it takes for light to travel one Planck length, about 10 to the negative 43 seconds, it represents a scale so far beyond our current reach that it feels almost abstract. To grasp just how small this is, consider that a femtosecond is already unimaginably brief, yet Planck time is some 10 to the 28 times smaller still. It is a scale where our current theories of physics, relativity and quantum mechanics, no longer play well together. Below this threshold, the smooth fabric of space-time may dissolve into something foamy and chaotic, something no clock, however perfect, could ever measure. This raises a strange paradox. Our clocks keep improving, our slices keep shrinking, but if Planck time is real, then the universe itself imposes a stop sign. No matter how clever we are, no matter how advanced our instruments, there may be a point beyond which the concept of a smaller moment is meaningless. The search for the fundamental limit is not just a technological quest. It is a philosophical one, a confrontation with the possibility that time, like matter or energy, comes in quanta, indivisible packets that cannot be subdivided further. The beauty of this pursuit is that it reflects the same impulse that guided humans from the beginning. When ancient people first marked shadows on the ground, they were already searching for a way to pin down time to make it tangible. Each step since, the water clock, the pendulum, the cesium atom, has been an act of refinement, a new way of saying, this is the measure of a moment. Now, as physicists push into attoseconds and zeptoseconds, they're continuing the same journey, driven by the same hunger to grasp what time really is. The difference is that today the journey has brought us close to the very edge of knowability, and even as we approach this edge, the questions only deepen. If Planck time marks the lower boundary, what does that say about the nature of reality? Does the universe tick in discrete beats, like a cosmic metronome too fast for us to hear? Or is it still continuous, with Planck time serving as more of a mathematical curiosity than a physical truth? These are not questions with easy answers, and they may remain unresolved until a theory uniting quantum mechanics and gravity is finally achieved. For now, the search continues in laboratories around the world. Scientists build ever more stable clocks, refine lasers capable of measuring unimaginably brief events, and look for ways to connect their observations to the deepest questions of cosmology. Each new breakthrough not only sharpens our practical tools, but also chips away at the boundary between what can be measured and what must be imagined. Somewhere at the end of this road lies the fundamental limit, whether it proves to be Planck time or something even stranger. And so, the age of atoms with cesium at its core becomes not an endpoint but a gateway. By giving us the ability to define the second with such stability, it opened the door to the pursuit of finer and finer slices. That pursuit in turn leads inevitably to the question of limits. Beyond cesium, beyond strontium, beyond the lasers that capture attoseconds, we find ourselves staring at a boundary drawn not by our tools, but by the universe itself. The search for that boundary is what carries us deeper, toward the strange and fascinating realm where time itself may dissolve. By the time humanity had moved from sundials to cesium clocks, from hours marked by bells to fractions of a second measured by atoms, it seemed as though there was no end to how finely time could be divided. Each advance brought another level of detail, another layer peeled away from the flowing fabric of reality. Scientists could measure femtoseconds and attoseconds. They could describe the fleeting passage of a photon across a molecule. They could count the oscillations of atoms billions of times in a single heartbeat. And yet, in the mathematics of physics, there was a whisper of something smaller still, something not just beyond reach, but beyond imagination. It was called Planck time, and it is thought to be the briefest possible interval of existence, the smallest tick the universe allows before the very meaning of time breaks apart. The idea of Planck time begins with a German physicist named Max Planck, who lived at the turn of the 20th century. He's remembered as the father of quantum theory, the man who first suggested that energy is not continuous, but comes in discrete packets, or quanta. In trying to explain how light is emitted by hot objects, he discovered a constant, now known as Planck's constant, that would go on to reshape physics. What Planck may not have realised at first was that his constant, together with a handful of others like the speed of light and Newton's gravitational constant, could be combined to create natural units, measurements that did not depend on human choices like hours or meters, but instead arose directly from the laws of physics. Among these natural units was a timescale so unimaginably small that it seemed to mark the very edge of reality itself. Planck time is defined as the time it takes for light, moving at its cosmic speed limit, to travel a distance of 1 Planck length. That length is about 1.6 times 10 to the negative 35 meters, so small that if you magnified a proton until it was the size of the observable universe, a Planck length would still be invisible, smaller than a single atom in that cosmic scale proton. The corresponding time, Planck time, is about 5.4 times 10 to the negative 44 seconds. Written out, that is 0.00, with 43 zeros before you reach the 54. It is so far beyond ordinary human experience that the words we use, seconds, fractions, decimals, hardly seem equipped to describe it. To put it in perspective, consider again the blink of an eye. It takes perhaps a third of a second, or about 300 milliseconds. A millisecond is a thousandth of a second. A microsecond is a millionth. A nanosecond is a billionth. Already we are dealing with scales so small that only computers and specialized instruments can perceive them. A femtosecond is a millionth of a billionth of a second, the time scale of molecular vibrations. An attosecond is a billionth of a billionth, the domain of electrons moving within atoms. A zeptosecond is a trillionth of a billionth, and we have just begun to measure phenomena that unfold on this scale. Each step downward is another 1,000-fold drop, another chasm opening beneath us. And then, beyond all of these, comes Planck time, still many orders of magnitude smaller than even a zeptosecond. If a zeptosecond were the size of the observable universe, Planck time would be the size of a single human breath within it. The gulf is that vast. What makes Planck time more than just a number, more than just an absurdly small unit, is what it represents. Physics tells us that below this scale, our current understanding of the universe cannot be trusted. General relativity describes gravity as the curvature of space-time, smooth and continuous, while quantum mechanics describes the subatomic world as governed by probabilities and uncertainty. Normally, these two frameworks coexist, each ruling its own domain. But at Planck scales, times and lengths as tiny as these, the two collide. Space-time itself is expected to become turbulent, foamy, fluctuating wildly under the rules of quantum uncertainty. The smooth fabric that Einstein described would tear into something chaotic, a frothing sea of possibilities. This is why Planck time is often described as the smallest meaningful interval. Below it, the very concepts of time and space lose their coherence. Asking what happens in half a Planck time is like asking what lies north of the North Pole. It is a question that the universe itself refuses to answer. And yet, the importance of Planck time is not confined to abstract thought experiments. It plays a crucial role in cosmology, in our attempts to understand the birth of the universe. According to our best theories, the universe as we know it began with the Big Bang, expanding from an unimaginably hot and dense state. For the first fraction of a second, conditions were extreme beyond anything we can reproduce. Physicists can trace the universe back to about 10 to the negative 36 seconds after the Big Bang, when cosmic inflation began, blowing up the universe at an exponential rate. But if we try to push our understanding further, down to the very first instant we reach the Planck time, before that our equations break down. We cannot say with confidence what the universe looked like, or even if the word looked makes sense. The Planck time marks the horizon beyond which our theories cannot see. It is strange to think that such an abstract idea, a number so small it cannot be directly measured, a moment so brief it defies imagination, could define the boundary of our knowledge. Yet that is what Planck time does. It tells us, here, at 10 to the negative 44 seconds, lies the edge of physics as we currently know it. Beyond here, a new theory is required, one that unites quantum mechanics with gravity. Until that theory exists, the Planck time stands as both a barrier and a beacon, reminding us of the limits of our understanding and beckoning us toward what lies beyond. The existence of a minimum time interval also raises profound questions about the nature of reality. If time truly comes in indivisible units, then the universe might not flow continuously, but instead tick forward in discrete steps, like frames in a film played so fast that it appears smooth. We do not experience this discreteness, if it exists, but it may underlie the fabric of everything we know. On the other hand, Planck time might not be a literal tick, but simply a scale at which our current mathematics fails, a signpost telling us that new ideas are needed. Physicists debate this point vigorously, and until experiments can probe closer to that boundary, the question remains open. What makes Planck time so fascinating is that it represents the ultimate culmination of the journey humanity began thousands of years ago, from the shadow of a stick in the ground, to the dripping of water, to the swing of a pendulum, to the vibration of cesium atoms, Each step has been about slicing time more finely, finding more precise intervals, and discovering new layers of structure in the process. Planck time is the imagined end of that road, the final slice beyond which there is nothing left to cut. It is the answer to the question, what is the shortest possible time? And even if we cannot measure it directly, its existence shapes how we think about the universe. It tells us that time, for all its flowing continuity in our lives, may have a bottom layer, a graininess that no technology can smooth away. It tells us that the Big Bang itself is shrouded behind a veil of 10 to the negative 44 seconds, a curtain we cannot pull back until new physics arrives. It tells us that the journey of precision, for all its triumphs, may ultimately collide with the limits of reality itself. Still, the search goes on. Physicists continue to build better clocks, probe shorter intervals, and imagine experiments that might bring us closer to Planck time. Perhaps one day a theory of quantum gravity will reveal what lies beneath, showing whether time truly has a smaller step, or whether it is continuous after all. Until then, Planck time remains both a mystery and a guidepost, a reminder of how far we have come and how much further there is to go. And so, in the story of shrinking intervals, Planck time is not the final word but the most tantalizing one. It invites us to wonder what it means for something to be the shortest possible, to imagine a universe where time itself is quantized, and to recognize that even in the smallest slice imaginable, there may still be secrets waiting to be uncovered. When we hear that Planck time is about 10 to the negative 44 seconds, it may sound like an arbitrary curiosity, a number plucked from the far edges of mathematics, useful for physicists, but detached from any tangible meaning. But what makes Planck time extraordinary is not simply its smallness, but the way it emerges naturally from the universe itself. It is not a value chosen by convention, as the second once was when tied to the rotation of Earth. Nor is it an invention of human culture like hours or calendars. Planck time is derived from constants of nature, quantities that seem to be written into the very structure of reality. In this sense, it is less a human invention and more a discovery, a recipe that reveals something deep about the way the cosmos is built. Max Planck himself did not set out to find the shortest time. What he was trying to do at the end of the 19th century was to make sense of how objects emit radiation when heated. His work led him to introduce a new constant, now called Planck's constant, symbolized by the letter H. This constant describes the scale at which quantum effects become noticeable. It tells us, in effect, that energy is not continuous but comes in discrete chunks, or quanta. For example, light of a certain frequency can only be absorbed or emitted in packets of energy equal to that frequency multiplied by Planck's constant. The constant is tiny, about 6.6 times 10 to the negative 34 joule seconds, but it has colossal implications. It marks the boundary between the classical world of smooth energies and the quantum world of discrete jumps. But Planck's constant is only one part of the recipe. The second ingredient is the speed of light, symbolized by c. Unlike Planck's constant, the speed of light is something we can at least imagine more easily. It is about 300,000 kilometers per second, or 186,000 miles per second, the ultimate speed limit of the universe. Nothing with mass can move faster, and all electromagnetic waves, from radio to gamma rays, travel at this speed in a vacuum. The speed of light appears in countless equations in physics, binding together space and time in Einstein's theory of relativity and defining the way energy and mass are interchangeable. The third essential ingredient is Newton's gravitational constant, symbolized by g. This constant is less familiar in daily life, but just as fundamental. It describes the strength of gravity, the attractive force between masses. Its value is about 6.7 times 10 to the negative 11 Newton meters squared per kilogram squared. Unlike the speed of light, which is enormous, or Planck's constant, which is tiny, G is extremely weak compared to the other fundamental forces. You can see this weakness by considering how easily you can lift a paperclip with a small magnet, overpowering the entire gravitational pull of Earth. Yet gravity's reach is infinite, and its presence is universal, shaping planets, stars, galaxies, and the structure of the cosmos itself. Planck realized that by combining these three constants, h, c, and g, he could create natural units of length, mass, and time. The process is called dimensional analysis. Essentially, it means finding a way to combine constants so that the units cancel out, leaving only the desired dimension. For Planck time, the recipe looks like this. Take Planck's constant, divide it by the speed of light squared, then divide by the gravitational constant, and finally take the square root. The result is about 5.4 times 10 to the negative 44 seconds. It is a number so small that it lies far beyond any direct measurement, yet it is not arbitrary. It arises inevitably once you ask, what is the time scale defined purely by the fundamental constants of the universe? This is what makes Planck time so profound. It is not tied to the peculiarities of our planet, as the second once was. It is not based on human convenience, as hours and minutes were. It is not even chosen for practical utility, as the definition of the meter once was when tied to the Earth's circumference. It is a scale that exists whether or not humans are here to name it. If there were physicists in some distant galaxy, with no knowledge of Earth, no concept of our seconds or minutes, but with an understanding of the same laws of physics, they would derive the same Planck time. In this sense, it is a truly universal measure, born not of culture, but of the cosmos. What is striking is how different the roles of these constants are, yet how naturally they converge in this one unit. Planck's constant brings in the graininess of quantum mechanics, telling us that energy cannot be infinitely divided. The speed of light brings in relativity, telling us that space and time are bound together by an ultimate speed limit. The gravitational constant brings in the weakness yet universality of gravity, telling us how mass shapes space-time. Alone, each constant describes one domain of physics. Together, they describe the scale at which all three domains, quantum mechanics, relativity, and gravity, collide. That collision is what makes Planck time so important. It is the point at which our current theories break down, where the smooth predictions of relativity and the probabilistic rules of quantum mechanics no longer agree. The beauty of this recipe is that it tells us something subtle about nature's architecture. Our ordinary experience of time and space is continuous and smooth. You can walk across a room, and there's no sense of gaps or grains in between. Yet when we take the constants that govern the deepest laws of physics and blend them together, they whisper that perhaps there is a lower bound, a smallest step that cannot be crossed. This is not something we can yet test directly, but the mathematics is suggestive. It says, at the intersection of quantum mechanics, relativity, and gravity, time is measured not in seconds or nanoseconds, but in Planck intervals. It is worth noting that this approach is not unique to time. Planck also defined a natural length, mass, and temperature using the same constants. The Planck length, about 10 to the negative 35 meters, is the smallest meaningful unit of distance. The Planck mass, about 22 micrograms, sounds tiny but is enormous compared to the mass of fundamental particles. The Planck temperature, about 100 million Kelvin, is so extreme that it dwarfs the hottest conditions we can create in laboratories. Each of these values is strange in its own way, but together they form a system of natural units that mark the limits of our current theories. In this sense, Planck time is not just a curiosity, but part of a broader picture, a set of natural scales that highlight the boundary between known physics and the unknown. They tell us where our models stopped working, not because we have made a mistake, but because the universe itself demands a deeper explanation. If we ever succeed in developing a theory of quantum gravity, a framework that unifies general relativity with quantum mechanics, it will almost certainly have something to say about Planck scales. Until then, Planck time stands as both a placeholder and a promise, a hint of what lies on the other side of our current understanding. It is fascinating to reflect on how constants of nature give rise to such insights. For centuries, constants were viewed as arbitrary numbers, fixed by the universe without explanation. Why should the speed of light be 300,000 kilometers per second rather than some other number? Why should Planck's constant be 6 times 10 to the negative 34? Why should gravity be so weak compared to electromagnetism? These are still open questions, but what is remarkable is that when we combine them, they produce values like Planck time, values that carry profound meaning. It suggests that the constants are not random, but parts of a coherent structure, puzzle pieces that, when fitted together, reveal the outlines of something deeper. And so, Planck time is not just the shortest possible interval in theory. It is a fingerprint of the universe, stamped into the fabric of physics by its most fundamental ingredients. The recipe is elegant, almost deceptively simple. Combine H, C, and G in just the right way, and out comes a number that seems to mark the edge of time itself. In that number lies the convergence of quantum theory, relativity, and gravity, the 3 great pillars of modern physics. In that number lies a boundary we cannot yet cross, but which calls to us all the same. What follows from this realization is a deeper exploration of what such a tiny time interval means for our understanding of reality. If Planck time truly is the smallest possible unit, then it reshapes how we think about continuity, causality, and the unfolding of events. If it is not, if it is only a mathematical artifact, then it still serves as a guidepost pointing us toward a more complete theory. Either way, the constants of nature have given us a recipe for humility, a reminder that even with all our progress, there are scales of time and space that remain far beyond our reach. When we first hear that Planck time is on the order of 10 to the negative 43 seconds, it is tempting to dismiss the number as simply abstract, too far removed from daily experience to mean anything. We are used to small numbers in certain contexts. We might think of a millisecond as small, or a nanometer as tiny, or perhaps a billionth of a second as vanishingly brief. But numbers like 10 to the negative 43 lie in a completely different realm. They are so extreme that our normal intuitions collapse. The human brain, after all, evolved to measure footsteps, days, and seasons, not the flickers of reality at its ultimate limits. And yet, part of the journey into understanding Planck time is the attempt to stretch our imagination toward this inconceivable smallness, to try, however imperfectly, to grasp what it means. The easiest place to start is with something familiar, like the blink of an eye. A blink lasts perhaps a third of a second, which is around 300 milliseconds. Already, a millisecond is a thousandth of a second, and most of us have no conscious perception of time that fine. We cannot distinguish 2 events separated by only a millisecond. But in technology, milliseconds matter. A computer processor can perform millions of operations in that time. A hummingbird's wings may beat dozens of times in a single blink, and a camera flash may last only a few milliseconds. What feels instantaneous to us is in fact full of structure at the millisecond level. Now shrink down another step. A microsecond is a millionth of a second. Imagine snapping your fingers. In the time it takes, light can circle the globe 7 times. But in a microsecond, light travels only 300 meters, about the length of a football field. Electronic circuits operate on microsecond scales, sending signals down wires at nearly the speed of light. Some insects' nervous systems react in microseconds, allowing them to dart away before a human hand can swat. It is already astonishing how much can happen in a millionth of a second. Smaller still is the nanosecond, a billionth of a second. At this scale, light travels only about 30 centimeters, roughly the length of a ruler. Computer processors now operate with clock speeds measured in gigahertz, meaning billions of cycles per second, each cycle lasting about a nanosecond. When engineers speak of nanoseconds, they are speaking of the pulses that drive modern technology, the invisible beats behind every digital operation. To us, a nanosecond feels like nothing, but in electronics, it is the tempo of the digital age. Then comes the femtosecond, a millionth of a billionth of a second. Here, light travels only a fraction of the width of a human hair. Femtoseconds are the domain of ultra-fast lasers, which can freeze chemical reactions as they unfold. In fact, the Nobel Prize in Chemistry in 1999 was awarded for using femtosecond spectroscopy to observe how atoms in a molecule move during a reaction. Processes once thought instantaneous, like the breaking of a chemical bond, were revealed to have their own duration, measurable in femtoseconds. Drop down again, and we reach the attosecond, a billionth of a second. In 1 attosecond, light travels less than the width of a single atom. Electrons moving around a nucleus, phenomena so quick they were long thought beyond reach, can now be probed with attosecond pulses. In 2023, the Nobel Prize in Physics went to researchers who developed methods to generate attosecond pulses of light, opening a window onto the world of electron dynamics. Attoseconds give us a sense that time can be sliced thin enough to follow even the fastest constituents of matter. But we are not done yet. In 2020, researchers measured a process that lasted about 247 zeptoseconds, a trillionth of a billionth of a second. That was the time it took for a photon to cross a hydrogen molecule. A zeptosecond is so small that light, the fastest thing in the universe, barely moves the length of a few hydrogen atoms during that interval. Measuring such a brief event required extraordinary ingenuity, but it showed that even zeptoseconds are not beyond human reach. At each step we can marvel at the scale, but what happens when we try to compare these units to Planck time? The gap is staggering. A Planck time is about 10 to the negative 43 seconds, while a zeptosecond is 10 to the negative 21. That is a difference of 22 orders of magnitude. To put that in perspective, the ratio between a zeptosecond and a Planck time is about the same as the ratio between a single second and the entire age of the universe multiplied many times over. Imagine how incomprehensibly long the age of the universe feels compared to a single heartbeat. That is how incomprehensibly brief Planck time is compared to a zeptosecond. Another way to think of it is through stacking scales. If you line up 1 billion zeptoseconds, you do not yet reach a microsecond. If you line up 1 billion microseconds, you have a second. And still, Planck time sits far below, 22 orders of magnitude smaller than the already unreachable zeptosecond. It is not simply that Planck time is small, it is that it lies in a different category of smallness altogether, a place where numbers cease to feel connected to anything familiar. We can also try analogies with distances. Light, travelling at 300,000 kilometers per second, covers a distance of about 30 centimeters in a nanosecond. In a femtosecond, it travels only a few hundred nanometers, about the size of a virus. In an attosecond, it moves less than an atom's width. But in a single Planck time, light travels only a Planck length, about 10 to the negative 35 meters. Compare that to the diameter of a proton, which is around 10 to the negative 15 meters. The difference is 20 orders of magnitude. If a proton were enlarged to the size of the observable universe, a Planck length would still be invisible, smaller than a single atom within that cosmic proton. That is how far below familiar scales Planck time exists. These comparisons reveal why physicists describe Planck time as unimaginably small. It is not just beyond our perception, it is beyond our ability to directly connect to experience. Every analogy breaks down under the weight of the orders of magnitude involved. We can climb down the ladder, seconds, milliseconds, microseconds, nanoseconds, femtoseconds, attoseconds, zeptoseconds. But the ladder simply ends, and Planck time lies in the abyss beneath, unreachable by even our most advanced instruments. And yet the fact that we can calculate it, that it emerges so naturally from the constants of nature, gives it meaning. It tells us something profound about the structure of the universe. It tells us that there may be a bottom to time, a place where slicing stops, where no smaller tick exists. Whether or not that is physically true, Planck time serves as the ultimate reminder of scale, the farthest frontier of smallness. For anyone listening, perhaps the most striking realization is this: every event you have ever experienced, every thought, every heartbeat, every breath, has unfolded across intervals that are vast compared to Planck time. Even the blink of an eye, so fast that we scarcely notice it, lasts trillions upon trillions upon trillions of Planck times. If Planck time were the only unit of measure, your entire life would consist of an unimaginably large number of these tiny intervals. In that sense, even though Planck time is beyond us, it silently underlies everything, like the pixels of a screen so small that they vanish into a seamless image. The question that naturally follows is why physics insists on a scale so extreme, and what it implies about the nature of time and space themselves. When we trace the scales of time downward, moving from seconds to milliseconds, from nanoseconds to femtoseconds, then further through attoseconds and zeptoseconds, it feels as though we are on a kind of staircase with no end. Each step leads to another, each smaller unit becomes a tool for observing faster events, and the horizon of measurement always seems to recede further away. But physics tells us that this staircase does not go on forever. It has a bottom step, and that step is the Planck time. To ask about shorter intervals is not just to ask for a finer ruler, but to ask for something that the universe itself does not appear to provide. It is not simply a technological limit, it is a conceptual one, woven into the nature of reality. To see why, we must return to the two great frameworks of modern physics: general relativity and quantum mechanics. General relativity, Einstein's masterpiece, describes the world on large scales. It tells us that gravity is not a force acting at a distance, but the curvature of space-time itself. Mass bends space-time, and that curvature guides the motion of planets, stars, and galaxies. Quantum mechanics, by contrast, rules the microscopic realm. It tells us that particles behave like waves, that their properties are defined by probabilities rather than certainties, and that the act of measurement plays a role in shaping outcomes. These two frameworks are spectacularly successful in their respective domains, tested by countless experiments and observations. Yet they do not fit together. Relativity treats space-time as smooth and continuous, a fabric that can be bent but not torn. Quantum mechanics, on the other hand, insist that everything has fluctuations, that uncertainty cannot be eliminated, and that fields are jittery and restless at all scales. For most of physics, this mismatch is tolerable. When we deal with planets or stars, quantum effects are negligible. When we deal with atoms or electrons, gravitational effects are negligible. But at the Planck scale, both matter. The extreme smallness of Planck time means that quantum fluctuations of space-time itself become significant. The smooth fabric envisioned by relativity is shredded by uncertainty, and the probabilistic rules of quantum mechanics no longer fit neatly into a background of continuous time. One way to think of it is to imagine trying to measure a smaller and smaller interval of time with a clock. Suppose we want to measure something shorter than a Planck time. To do so, we would need a clock with parts moving fast enough and small enough to distinguish that interval. But the physics of building such a clock runs into contradictions. To measure such a short time, the energy involved in the ticking of the clock would be so great that it would collapse into a black hole. The act of trying to peer beneath a Planck interval would erase the very information we sought to capture. This idea can be illustrated by the so-called Heisenberg uncertainty principle. It tells us that the more precisely we try to measure one quantity, like position, the less precisely we can measure its partner, like momentum. The same logic applies to time and energy. To measure an event within an interval shorter than a Planck time, the uncertainty in energy would be so enormous that space-time itself would be destabilized. What we would get is not a sharper picture, but a chaotic storm where the concept of a well-defined time no longer exists. This is why physicists say that Planck time is not just a small number, but the smallest meaningful unit. Below it, the mathematics we rely on collapses. Relativity cannot handle the fluctuations. Quantum mechanics cannot handle the gravitational curvature. The two pillars of modern physics, which work so well separately, undermine each other in this realm. To go shorter would require a new theory, one that unites quantum mechanics and gravity into a single coherent framework. This hypothetical theory is often called quantum gravity, but it does not yet exist in a complete and experimentally verified form. The situation is not unlike trying to zoom in on a digital image. At first, each increase in magnification reveals more detail, but at some point you reach the level of individual pixels, and the image stops resolving further. Asking for more detail below the pixel level is meaningless, because the image simply does not contain it. Planck time plays the role of those pixels in the universe. It marks the scale at which asking for a shorter duration is like asking for half a pixel. The concept itself ceases to apply. Another way of approaching the problem is through the idea of Planck energy. Associated with Planck time and Planck length is a natural unit of energy, around 10 to the 19th billion electron volts. That is unimaginably larger than the energies reached in particle accelerators like the Large Hadron Collider, which probe up to around 10 to the 12 billion electron volts. If we were to attempt to probe events at Planck timescales, we would need energies on the order of the Planck energy, far beyond anything we can produce. At such energies, the density of matter and energy would be enough to form black holes spontaneously. The very act of investigation would destroy the system we were trying to observe. This is not just speculation. It has real consequences for cosmology. When physicists trace the history of the universe back toward the Big Bang, they can describe events with confidence down to about 10 to the negative 36 seconds, the beginning of cosmic inflation. But beyond that lies the Planck epoch, the time before 10 to the negative 43 seconds. At that point, our equations cannot be trusted. They churn out infinities and contradictions. They tell us nothing reliable about what happened. This is not because the universe did not exist, but because our theories cannot describe it. Physics, as we know it, stops at the Planck time. The implication is that the universe itself enforces a limit. Just as nothing can travel faster than the speed of light, no event can be said to happen in less than a Planck interval. It is a kind of cosmic censorship, a way the laws of nature protect themselves from paradox. We can calculate Planck time because it emerges from the constants of nature, but we cannot meaningfully subdivide it. To try is to fall into contradictions where space, time, matter and energy lose their definitions. Some physicists interpret this as evidence that time itself is quantized, that it comes in discrete steps rather than flowing smoothly. In this view, Planck time is the smallest indivisible unit, like an atom of time. Others caution against taking the idea too literally. Planck time may not be a real tick of the universe, but simply the scale where new physics becomes necessary. Until a theory of quantum gravity is found, we cannot know which interpretation is correct. What we do know is that within our current theories, the question of shorter intervals is not just unanswered, but unanswerable. And so, when physicists say we cannot go shorter than Planck time, they are not imposing an arbitrary rule. They are acknowledging the breakdown of the frameworks that have otherwise described nature with astonishing accuracy. It is a limit not of imagination but of consistency. The equations themselves draw the boundary. To cross it, we will need new mathematics, new insights, perhaps even a revolution in how we think about time. Until then, Planck time remains the edge of our map, the place where the known ends and the unknown begins. When we imagine space and time, we usually picture them as smooth. Space feels like an endless stage on which objects sit and move. Time feels like a steady current, flowing evenly from one moment to the next. Einstein's theory of general relativity embraced this intuition, describing space-time as a continuous fabric, curved by mass and energy but still fundamentally smooth. On everyday scales, this picture works beautifully. It predicts the orbits of planets, the bending of light around galaxies, the way black holes shape the cosmos. Yet as we approach the Planck scale, the smallest units defined by nature's constants, this familiar smoothness begins to break apart. The world there is not a calm fabric, but a frothing ocean. Physicists sometimes call it the quantum foam, a restless, bubbling, jittering state where space-time itself cannot hold still. The idea of quantum foam comes from trying to apply quantum mechanics not just to particles and fields, but to space-time itself. Quantum mechanics teaches us that nothing is ever completely at rest. Even in a perfect vacuum, particles and antiparticles flicker into and out of existence. This is called quantum fluctuation, and it is unavoidable. If you could somehow remove every bit of matter and energy from a region of space, there would still be activity, virtual particles popping in and out, borrowing energy from the void, and then disappearing. This restless quality is built into the uncertainty principle, which insists that energy and time cannot both be defined with absolute precision. The shorter the timescale, the larger the uncertainty and energy. At Planck timescales, this uncertainty becomes overwhelming. In an interval as short as 10 to the negative 43 seconds, fluctuations in energy become so large that they curve space-time violently. Instead of the gentle curves described by relativity, space-time buckles and twists, forming miniature distortions, wormholes, and even tiny black holes that appear and vanish. These structures exist for only a Planck time before dissolving, but during that fleeting instant they warp the geometry of the universe. The picture is not of a smooth fabric, but of a foam, frothing and seething like the surface of a boiling pot. That is the quantum foam. It is important to emphasize that quantum foam is not something we can observe directly. It is a theoretical consequence of trying to merge quantum mechanics with general relativity. Neither theory alone gives rise to foam, but together, at the Planck scale, their demands produce a vision of space-time in turmoil. This means that the foam is not just a metaphor but a necessary implication of the mathematics. If space-time is subject to quantum uncertainty like everything else, then at tiny scales it must fluctuate wildly. The scale of these fluctuations is hard to convey. A wormhole in the quantum foam would not be like the science fiction portal spanning galaxies. It would be smaller than a proton by 20 orders of magnitude, and it would last for only a Planck time before collapsing. A black hole in the foam would not devour stars but would vanish almost as soon as it formed, radiating away its energy through processes described by Stephen Hawking. These phenomena are not the grand features of the universe we usually think of, but miniature, ephemeral flickers. And yet, taken together, they define the character of reality at its deepest level. One way to picture it is to imagine the ocean. From a distance it looks flat and calm, a smooth surface stretching to the horizon. But up close the surface is anything but smooth. It ripples, foams and bubbles constantly. Quantum foam suggests that space-time itself behaves the same way. From a human vantage point spanning meters and seconds, it seems continuous and serene. But if we could zoom into the scale of Planck lengths and Planck times, we would see a frothy chaos, with space-time itself bubbling in and out of configurations. The concept of quantum foam raises unsettling questions about the nature of reality. If space-time is not continuous, what does it mean to move smoothly through it? If time is not a steady flow but a jittery progression of intervals, how do we experience continuity? Our entire existence seems to rely on the idea that events unfold smoothly, but the foam suggests that this is an illusion, a large-scale average of countless fluctuations. Just as the surface of a lake looks smooth from far away, so too does space-time appear smooth when viewed across many Planck units. The foam is hidden beneath, inaccessible but essential. Quantum foam also highlights why we cannot measure below Planck time. Any attempt to probe smaller intervals would be swallowed by the turbulence. The very notion of shorter loses meaning when space-time itself is flickering out of recognizable form. It is like trying to draw a straight line on a piece of paper that is constantly crumpling and dissolving beneath your pencil. The act of measurement presumes stability, but in the foam, there is no stability to be had. Although the foam itself cannot be observed directly, its possible consequences ripple outward into physics and cosmology. Some researchers have speculated that the foam might leave faint imprints on the light travelling across the universe. Photons travelling billions of light years could be subtly scattered by the fluctuations, producing effects we might one day detect with ultra-sensitive telescopes. Others suggest that the foam may play a role in the emergence of space and time themselves, that the smooth space-time of relativity is not fundamental, but an approximation built atop the seething foam. In this view, the foam is not just noise at the bottom of reality, but the foundation upon which reality is built. The foam is also central to many approaches to quantum gravity, the yet unknown theory that would unite relativity and quantum mechanics. String theory, for example, envisions tiny vibrating strings replacing point-like particles, with extra dimensions curled up at the Planck scale. Loop quantum gravity imagines space-time itself as made of discrete loops, woven together into a network that approximates smoothness at larger scales. Both approaches, though very different, echo the idea that beneath the surface space-time is not smooth. It is granular, foamy, restless. The exact details differ, but the message is the same. At the Planck scale, the calm fabric gives way to something far stranger. Reflecting on quantum foam is both humbling and exhilarating. It is humbling because it reminds us that our most basic intuitions, that space is continuous, that time flows evenly, are likely only approximations. It is exhilarating because it suggests that there is still so much to discover, that reality holds layers of complexity hidden far beneath our current reach. The foam is not directly visible, yet it may be the most fundamental thing of all. It is the stage upon which particles dance, the background hum of existence, the grain from which smoothness emerges. And so, when physicists speak of the quantum foam, they are not indulging in science fiction but following the demands of their theories to their logical extreme. If quantum mechanics governs all of nature, then space-time cannot be exempt. If uncertainty applies everywhere, then it applies to the fabric of reality itself. The result is a universe that, at its deepest level, is not calm but flickering, not smooth but foamy. It is a universe forever restless at its foundations, even as it appears serene from afar. When we talk about the Big Bang, we often imagine it as an explosion, a single instant when everything burst outward from a tiny point into the vastness we see today. But this picture is at best a simplified metaphor. The Big Bang was not an explosion in space. It was the expansion of space itself. Time, space, matter, and energy were not merely inside the event, they were the event. And at the very earliest instant, at times shorter than 10 to the negative 43 seconds, we encounter a realm known as the Planck era. It is the domain where our current theories cannot tell us what happened. We can trace the universe backward with equations of cosmology, back through billions of years of expansion, back through the formation of galaxies and stars, back even through the fusion of the first light elements. But as we reach earlier and earlier times, the story becomes more speculative. At 1 second after the beginning, we can be fairly confident. At a millionth of a second, we still have reasonable theories. At a trillionth of a second, we can use particle physics to describe conditions. But once we cross the boundary of 10 to the negative 43 seconds, we enter the Planck era, and there the map of physics goes blank. To appreciate why, we need to think about what the universe was like in those unfathomably early moments. Today, the cosmos stretches across almost 100 billion light-years, filled with stars, galaxies, planets, and dark matter. It is vast and relatively cool, with an average temperature just a few degrees above absolute zero. But in the earliest instance, the universe was unimaginably hot and dense. All the matter and energy of the cosmos were compressed into an incredibly small volume, perhaps smaller than an atom, perhaps even smaller than a proton. The density was so extreme that the known forces of nature may not have been separate. The four forces we recognize today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified into a single force. In that regime, the temperature of the universe was around 10 to the 32 Kelvin, the Planck temperature. That is not just hot in the sense of a burning star or a nuclear explosion. It is a temperature so extreme that the very concept of temperature begins to blur. Temperature, after all, is a measure of the average energy of particles, but when the average energy of particles approaches the Planck energy, around 10 to the 19th billion electron volts, then the particles themselves may no longer be well defined. At such conditions, space and time themselves may have fluctuated violently, foaming and bubbling in ways we cannot yet model. The Planck era is not simply a smaller, hotter version of the later universe. It is a fundamentally different environment. The equations of general relativity, which describe gravity on cosmic scales, break down when energy densities reach the Planck level. Quantum mechanics, which describes the behavior of particles, also becomes inadequate because it does not include the effects of gravity. At the Planck scale, quantum fluctuations of space-time itself dominate. The smooth geometry of relativity is shredded by uncertainty. It is here that we encounter the need for a theory of quantum gravity, a framework that would merge the principles of relativity and quantum mechanics into a single coherent description. Without such a theory, we cannot know what truly happened in the Planck era. What we can say, however, is that the Planck era marks the limit of our knowledge. It is the horizon beyond which our theories cannot see. Just as the event horizon of a black hole marks the boundary beyond which light cannot escape, the Planck era marks the boundary beyond which our mathematics collapses. Every description we attempt leads to infinities or contradictions. Was the universe infinitely dense? Did time itself begin there? Was there a singularity, a point of zero size containing all the mass and energy of the cosmos? These are the questions that haunt cosmology, and the answers remain hidden behind the veil of the Planck time. One of the most intriguing possibilities is that during the Planck era, space-time was dominated by the quantum foam. Instead of a smooth, expanding fabric, the universe may have been a storm of fluctuating geometries, with tiny wormholes and miniature black holes popping in and out of existence. If so, then the smooth universe we inhabit today is like the calm that emerges after turbulence, an average over the chaos of its first moments. This idea suggests that what we call the Big Bang may not have been a single point of origin, but the outcome of deeper processes at the Planck scale. Perhaps the foam gave rise to inflation, the rapid exponential expansion that smoothed out the universe. Perhaps the foam is still with us, shaping space-time at the smallest scales, though hidden from direct view. It is also possible that the Planck era was not the beginning at all. Some theories suggest that time may extend before it, that the Big Bang was not a singular birth, but a transition from a prior state. In cyclic models, the universe may undergo endless expansions and contractions, with each bounce passing through something like the Planck era. In multiverse models, our Big Bang may have been the budding of one universe from a larger foam of universes, each with its own laws and constants. These are speculations, but they illustrate how the Planck era forces us to confront possibilities beyond ordinary physics. The importance of the Planck era lies not only in what happened then, but in what it implies about the limits of science. When we say that our knowledge stops at 10 to the negative 43 seconds, we are acknowledging that the universe contains domains beyond our current reach. That does not mean they are forever unknowable. It may be that future theories, future observations will shed light on those earliest instants. But for now, the Planck era stands as a boundary between the known and the unknown, a frontier that humbles us even as it inspires us. And so, when we imagine the Big Bang, it is not enough to picture an explosion or a sudden burst of light. We must also imagine a time before time as we know it, a state where the laws of physics dissolve, where space and time themselves were in flux, where the universe existed as a flickering foam of possibilities. This is the Planck era, the realm that lies beneath our equations, the first instant of everything, and the deepest mystery in cosmology. From here, the natural question is what happened as the universe emerged from that state, how the smooth expansion we observe today grew out of such a chaotic beginning, and what it means to say that time itself was born in that earliest flicker. When we try to imagine the birth of time, we immediately encounter a paradox. To speak of a beginning is already to place events within a timeline, yet if time itself was what began, then the word before loses its meaning. Our minds are built to think in sequences. One thing follows another. Past leads to present. Present leads to future. But when cosmologists trace the story of the universe back to the Planck era, they find themselves at a horizon where that sequence collapses. The very dimension of time which lets us tell stories, measure change, and hold memory seems to have emerged at that boundary. Asking what came before may be as meaningless as asking what lies north of the North Pole. The coordinate simply does not exist. The question of when time was born is therefore tied intimately to the nature of the Big Bang itself. The prevailing view in physics is that the Big Bang was not an explosion in space, but the expansion of space and time together. This means that time itself did not flow before the event, it came into being with it. Just as the universe expanded spatially from an unimaginably dense state, so too did it expand temporally from a moment of zero duration. What we call the beginning is the beginning of both space and time. Einstein's general relativity is crucial here. His equations describe the geometry of space-time, how mass and energy curve it, and how it evolves. When we trace those equations backward through cosmic history, we see space-time itself shrinking until it reaches a singularity, a point of infinite density and zero size. At that singularity, the equations break down. They do not merely fail to give answers, they give nonsensical answers. Infinities where none should exist. This breakdown is what signals that the concept of time as we know it ceases to apply. The singularity is not a place in time, but the limit of time itself. And yet, while relativity tells us that time begins at the Big Bang, quantum mechanics complicates the picture. Quantum theory does not like singularities. It insists on uncertainty, on fluctuations, on probabilities rather than infinities. This has led many physicists to believe that the singularity is not real but a symptom of our incomplete theories. Instead of a sharp beginning, there may have been a transition. Time may not have been created from nothing but may have emerged gradually from a timeless state, a realm where quantum gravity rules. What would it mean to have a timeless state? Imagine trying to describe a world without before and after. In such a world, change does not unfold, because unfolding itself requires time. Instead, everything might exist as possibilities, not yet ordered into sequence. Some researchers imagine this as a quantum superposition of states, where the universe exists in many forms at once without a timeline to sort them. Time, in this view, is not fundamental but emergent, arising only when the universe reaches a scale large enough and stable enough for sequences to make sense. Just as temperature is not defined for a single particle, but only for large ensembles, time may not be defined at the smallest scales but only for the universe as a whole. This perspective has given rise to proposals like the Hartle-Hawking no-boundary model. In that model, developed by James Hartle and Stephen Hawking, the universe does not begin with a singularity but with a smooth, rounded geometry that is finite but without boundary. Just as the surface of the Earth is finite yet has no edge, the early universe may have been finite without a beginning in the ordinary sense. In this model, asking what came before is as meaningless as asking what lies south of the South Pole. Time, in this vision, emerges from a more fundamental geometry, unfolding like a new dimension as the universe expands. Whether through the no-boundary idea or other models, the underlying suggestion is that time may have been born not as a sudden instant, but as a transition from timelessness to temporality. In that sense, the birth of time is less like the striking of a clock and more like the gradual brightening of dawn, when darkness gives way to light so smoothly that no single moment can be called the first. This raises profound questions not only about physics but about our own understanding of existence. If time itself has a beginning, then everything we know, memory, causality, history, is contingent upon that beginning. The universe did not simply start in space, it started in time. Every chain of cause and effect, every sequence of thought, every tick of a clock is rooted in that primal emergence. The fact that time had a birth suggests that it may also have a character we do not yet understand, perhaps even a destiny. For listeners, it can be helpful to imagine the early universe as a film reel that starts with a blank screen. The first frame is not just the first event, it is the frame that creates the possibility of events at all. Without that frame, there is no reel, no story, no sequence. That first frame is the birth of time. What it looked like we do not yet know. Was it turbulent, with quantum foam giving way to expansion? Was it smooth, with geometry unfolding seamlessly? Was it part of a cycle, a bounce from a prior collapse? Each possibility reflects a different vision of how time might begin, but all point to the same truth, that the time we inhabit, the flow we take for granted, has not always been there. It arose. The recognition that time had a birth has a disorienting effect on the imagination. It forces us to accept that before the Big Bang is not a legitimate question. And yet, as humans, we cannot help but ask it. We want to know what was before. Was there nothing? Was there another universe? Was there a timeless state, a sea of potentialities? This tension between what physics says and what our minds want to imagine is part of the mystery. It is why cosmology is not just a science of numbers, but also a deeply philosophical endeavour. And here lies the connection to Planck time. That smallest measurable unit marks the earliest instant at which time, as a physical dimension, makes sense. Before that, time as we understand it does not exist. At 10 to the negative 43 seconds we can begin to speak of intervals. Before that we cannot. It is not that nothing happened, but that the concept of happening loses its meaning. Planck time is therefore not only a boundary for physics but also a boundary for thought. It is where the questions we know how to ask dissolve into questions we do not yet know how to frame. Thinking about the birth of time is not only about the cosmos but also about perspective. Every moment we live is made possible by that initial emergence. Every laugh, every breath, every heartbeat rests on the fact that time exists at all. The birth of time is the birth of possibility, the opening of a stage upon which everything else unfolds. Without it, there would be no stars, no planets, no life, no awareness. In that sense, to contemplate the birth of time is to contemplate the root of existence itself. And as the universe expanded and cooled beyond that first instant, time began to stretch, acquiring the regularity that allowed structures to form, atoms to combine, galaxies to coalesce. From its mysterious birth at the Planck scale, time became the steady backdrop of cosmic history. What began as an emergent property of quantum fluctuations became the arena of stars and galaxies. What began as a flicker became the flow we now inhabit. And the story continues forward, carrying us with it, inviting us to wonder where this river of time is heading. When we talk about the Planck time, the smallest meaningful slice of duration, it's tempting to imagine that all we need is a better stopwatch, a finer instrument, and we could peer into it directly. After all, so much of scientific progress has come from building better tools. Telescopes let us see stars invisible to the naked eye. Microscopes revealed a hidden world of cells and bacteria. Particle accelerators opened up the subatomic realm. Each time we thought we had reached the edge, new instruments pushed it back. It's natural then to wonder, why not simply build a clock precise enough to measure intervals shorter than 10 to the negative 43 seconds? The reason is that nature does not cooperate with that plan. At scales approaching the Planck time, the very act of trying to measure destroys the possibility of measurement. The problem is not just that our tools are too crude, but that the laws of physics themselves prevent us from looking closer. It is as if the universe has drawn a curtain, not of technology, but of principle. Consider first what it means to measure time. A clock is, at its core, a device that marks regular intervals. The swing of a pendulum, the oscillation of a quartz crystal, the vibration of atoms in a cesium fountain. Each provides a repeating process that we can count. To measure smaller intervals, we need faster oscillations. Today's most precise atomic clocks measure time by observing transitions in atoms that oscillate billions of times per second. This allows them to keep time with staggering accuracy, losing less than a second over billions of years. But even these clocks are still eons away from Planck scales. To reach 10 to the negative 43 seconds, we would need an oscillator that cycles not billions of times per second, but 10 to the 43 times per second. That number is so large that it doesn't even correspond to anything in our physical world. There is no particle, no field, no system that ticks that quickly. But suppose, in a thought experiment, we tried to build such a clock. The problem we would face is energy. To confine oscillations to Planck timescales, the uncertainty principle tells us that the energy involved would have to be immense, on the order of the Planck energy. That is around 10 to the 19th billion electron volts, far beyond the energies in our most powerful particle colliders. If we tried to gather that much energy in a small enough region to probe Planck times, gravity would take over. The energy density would be so high that it would collapse into a black hole. Instead of a clock, we would create an object from which no information could escape. Our effort to measure would erase the very thing we wanted to measure. This interplay between quantum uncertainty and gravity is at the heart of why Planck time is a limit. In ordinary physics, we can keep dividing intervals smaller and smaller because the systems we use to measure them remain stable. But at the Planck scale, stability itself vanishes. Any attempt to peer closer summons energies and curvatures so extreme that space-time folds in on itself. The measuring rod crumbles, the stopwatch implodes, the notion of before and after dissolves. It is not a matter of engineering, it is a matter of definition. Think of trying to measure the thickness of a sheet of paper with a ruler made of bricks. The ruler is simply too coarse. But unlike that example, where we could always make a finer ruler, the Planck scale is different. Here, every attempt to make the ruler finer leads to paradox. The uncertainty principle says that if we confine a particle to a region small enough to probe the Planck length, or Planck time, the momentum becomes so uncertain that the particle's energy explodes. That energy curves space-time to such an extent that we can no longer speak of a stable background against which to make the measurement. It's as though the ruler erases the paper the moment it tries to measure it. This is why Planck time is not just small but final. It represents a limit where our methods of measurement and the very concepts behind them fail. In practice, this means that experiments cannot, even in principle, reach that scale. The finest experiments in high-energy physics probe down to lengths of about 10 to the negative 20 meters, corresponding to timescales of around 10 to the negative 20 seconds. That is staggeringly small, far beyond anything in daily life, but it is still 20 orders of magnitude away from the Planck time. That gap is not just technological but fundamental. Closing it would require energies and densities that collapse into black holes, erasing the experiment. This limit has fascinating implications. It suggests that the universe has a built-in granularity, a smallest tick that is unreachable to observation. It's as if the cosmos has decided that below a certain threshold, asking questions is meaningless, and yet those questions still press on us. What does space-time look like beneath the Planck curtain? Is it foamy, discrete, woven from loops or strings? Is it continuous but unstable, flickering in ways we cannot yet model? The inability to measure does not erase the curiosity, it only sharpens it, pushing us toward new theories that might describe what cannot be observed directly. Some physicists hope that indirect signatures might still reveal Planck-scale physics. For example, light travelling across billions of light years might accumulate tiny distortions from quantum fluctuations in space-time. If such distortions exist, they might show up as subtle blurring of distant galaxies or irregularities in gamma-ray bursts. Detecting such effects would be like inferring the presence of foam from the way light scatters off it, without ever seeing the foam directly. But so far, no such evidence has been confirmed. The Planck scale remains hidden, a horizon of knowledge rather than a frontier we can cross. It is worth noting that these limits are not frustrating failures but profound clues. The fact that measurement itself breaks down at the Planck scale tells us something important about the structure of reality. It tells us that space-time is not infinitely divisible, that the continuous fabric described by relativity cannot extend forever into smaller and smaller intervals. There is a flaw, and it is set not by our imagination but by the constants of nature themselves. The speed of light, the gravitational constant, Planck's constant. These numbers, woven together, dictate the boundary. To ask why we can't measure below it is to ask why those constants have the values they do, and that is a question as deep as any in science. If anything, the limits of measurement remind us that the universe is not infinitely transparent. It has mysteries it guards behind walls of principle. We can glimpse the outlines of those mysteries through mathematics, through thought experiments, through indirect effects. But the direct window remains closed. This is humbling, because it reminds us that there are aspects of reality beyond the reach of our instruments. It is also inspiring, because it tells us that there are still domains of knowledge waiting for new ideas, new frameworks, new ways of seeing. So when physicists say we cannot see down to the Planck time, they are not simply throwing up their hands. They are describing a boundary that is woven into the cosmos itself. A limit that is not a challenge to overcome but a definition to respect. It is the edge of measurement, the place where our rulers and clocks dissolve, the place where the universe itself whispers, no further. And from there, the mind can only imagine what lies beneath, a realm where space-time foams and flickers, where the familiar flow of time is not yet born, where reality itself reshapes its rules. When we picture the most mysterious objects in the cosmos, it is often black holes that come to mind. They are regions of space where gravity is so strong that nothing, not even light, can escape. They are born when massive stars collapse at the end of their lives, squeezing their matter into a volume so small that escape is impossible. But beyond being exotic celestial objects, black holes are also windows into the nature of time itself. They show us that time is not as steady and universal as we once believed, but something that can be stretched, slowed, and in some places shredded altogether. To begin understanding this, we need to recall that Einstein's general relativity tells us space and time are not separate entities but part of a unified space-time. Mass and energy curve this space-time, and that curvature tells objects how to move. Near Earth, this curvature is gentle, giving rise to the familiar pull of gravity. Near a black hole, the curvature becomes so extreme that the very structure of space-time bends back on itself. The surface around a black hole from which nothing can escape is called the event horizon. Crossing this horizon is crossing a point of no return. From the outside, nothing beyond it can be observed. But the event horizon is not only a boundary of space, it is a boundary of time. For a distant observer watching an object fall toward a black hole, time appears to slow. The closer the object gets to the event horizon, the slower its motion becomes, until it seems to freeze just at the horizon. Light from the object is stretched to longer and longer wavelengths, fading into invisibility. To the outside observer, the object never quite crosses. From the perspective of the falling object, however, it crosses the horizon in finite time, without noticing anything unusual. Two descriptions, equally valid, but radically different. Time near a black hole is not universal but relative to where you are. This relativity of time becomes even stranger inside. According to general relativity, once inside the event horizon, all possible paths lead inward. Space and time effectively trade roles. The singularity at the centre, a point of infinite density, becomes not a place you might reach someday, but a moment in your future, unavoidable once you have crossed the horizon. Just as you cannot avoid tomorrow, you cannot avoid the singularity. In this sense, time inside a black hole is shredded, directed inexorably toward an endpoint. It is not just space that collapses, but the timeline itself. The connection between black holes and Planck time emerges when we think about what happens at the singularity. Relativity predicts infinite curvature, infinite density, infinite tearing of space-time. But infinities in physics are usually a sign that our theories have reached their limits. At scales approaching the Planck length and Planck time, quantum mechanics must play a role. The singularity is where relativity demands certainty, but quantum mechanics demands uncertainty. It is the place where time itself, as we understand it, may dissolve into quantum foam. Black holes are not just theoretical curiosities, they force these issues upon us. In the 1970s, Stephen Hawking showed that black holes are not completely black. Quantum fluctuations near the event horizon cause them to emit radiation, now called Hawking radiation. This means black holes slowly lose mass, and over immense spans of time evaporate away. Here, quantum mechanics and relativity interact directly, producing a paradox. If black holes evaporate, what happens to the information about the matter that fell in? Does it vanish, violating the principle that information is preserved in physics? Or is it somehow encoded in the radiation? This so-called information paradox is still unresolved, and at its core lies the tension between time as relativity describes it, and time as quantum mechanics demands it. The shredding of time near black holes is not limited to singularities. Even outside the horizon, time is distorted. Imagine two twins, one remaining far from a black hole and the other orbiting close to its horizon. When they reunite, the twin who lingered near the black hole will have aged less. Time literally flows differently depending on the strength of gravity you experience. This is called gravitational time dilation, and it has been measured in experiments here on Earth. Atomic clocks placed at different altitudes tick at slightly different rates because of Earth's gravity. Near a black hole, the effect becomes extreme. A few hours close to the horizon might correspond to centuries for a distant observer. This is not science fiction. It is the direct consequence of how gravity shapes time. In this way, black holes act as natural laboratories for the study of time. They reveal that time is not a universal backdrop, but a participant in the dynamics of the universe. They also show us that at the extreme edges of physics, time breaks down. The shredding of time at singularities is not something we can ignore, because it signals that our theories are incomplete. It demands a new framework, one that unifies quantum mechanics and relativity, one that explains what happens to time at the Planck scale. Speculative theories attempt to describe this. In loop quantum gravity, the singularity might be replaced by a bounce, where the collapse of space-time halts at the Planck scale and rebounds. In string theory, the singularity may be smoothed out by extra dimensions and fundamental strings. In some approaches, time itself is not fundamental but emergent, arising only from the collective behaviour of more basic entities. Each of these theories is trying to answer the same question: what does it mean for time to end? The fascination with black holes is therefore not only about their exotic nature, but about the way they force us to confront the fragility of time. They show us that time can slow, stretch, twist, and even stop, depending on perspective. They suggest that time might not be an unbroken flow, but something that can collapse under the weight of gravity. They remind us that the smooth timeline we rely on may not be universal, but contingent, vulnerable to being shredded under the right conditions. As we reflect on this, it is important to remember that black holes are not rare oddities. The centres of galaxies harbour supermassive black holes, millions to billions of times the mass of the Sun. Stellar mass black holes populate our galaxy. If time can be stretched and shredded around these objects, then the universe is filled with regions where the flow of time is not what we experience. The cosmos is not governed by a single rhythm, but by many, depending on where gravity holds sway. The story of black holes is therefore deeply connected to the story of Planck time. Both mark boundaries in our understanding of time. Planck time marks the smallest slice of duration we can meaningfully describe. Black holes mark regions where time itself bends and collapses. Both show us that time is not absolute, but shaped by the fabric of the universe. And both point toward the need for new physics, a deeper understanding of how gravity and quantum mechanics together define the essence of time. And so, when we think of black holes, it is not only the darkness we should imagine, not only the crushing gravity, but the strange and fragile fate of time itself. A clock near a black hole is not the same as a clock far away. An observer falling inward does not share the same history as an observer remaining outside. At the horizon, perspectives diverge so drastically that time itself becomes relative, shredded into viewpoints that cannot be reconciled. The black hole is a mirror held up to the universe, showing us that time is not uniform but fragile, not absolute but mutable, not eternal but subject to being bent and broken. And beyond the event horizon, in the depths where singularities reside, lies the unanswered question: what is time when it can no longer be measured, when space-time itself ceases to provide a stable framework? It is there, in the shredding of time at the heart of black holes, that we sense the same mystery that hovers at the Planck scale, a mystery still waiting for an answer. When scientists talk about the Planck scale, the Planck time, or the collapse of space and time near black holes, they often acknowledge a central truth: our current theories are not enough. General relativity is magnificent in its ability to describe gravity, stars, galaxies, the bending of light, the dynamics of the cosmos at large. Quantum mechanics is equally magnificent in describing the microscopic world, the behaviour of particles, atoms, and the fields that govern them. Each theory is tested, precise, and reliable in its own realm. But when we bring them together, when we ask about the birth of time, or the singularity of a black hole, or the fabric of space-time at 10 to the negative 43 seconds, they clash. They produce contradictions, infinities, impossibilities. This is why physicists search for something deeper, a theory that unites them. Two of the most compelling approaches are string theory and loop quantum gravity. They are different in their language, different in their assumptions, but both are driven by the same question: what lies beneath space-time as we know it? String theory begins with a radical idea. Instead of treating the fundamental building blocks of nature as point-like particles, it proposes that they are tiny, one-dimensional strings. These strings vibrate at different frequencies, and the vibration determines what kind of particle they appear to be: a photon, an electron, a quark. In this view, each is simply a different mode of vibration of the same kind of fundamental string. It is an elegant unification, reducing the zoo of particles to a single underlying entity. But what makes string theory especially powerful is that it naturally includes gravity. One of the vibrational modes of the string corresponds to a particle called the graviton. the hypothetical quantum of gravity. In this way, string theory is not only a unification of particles but also a unification of forces. It promises to merge quantum mechanics and relativity into a single framework. At the Planck scale, instead of infinite singularities, string theory suggests that the extended nature of strings smooths things out. The collapse into zero size is avoided because strings cannot shrink beyond their own length. Time and space, instead of dissolving into infinities, may emerge from the dance of these vibrating filaments. Of course, strings come with extraordinary demands. For the mathematics to work, string theory requires extra dimensions of space, far more than the 3 we are familiar with. In some versions there are 10 dimensions, in others 11. These extra dimensions are thought to be curled up, compactified into shapes too small to observe directly. They may be folded into intricate geometries called Calabi-Yau manifolds, hidden from view but crucial to the vibrations of strings. It's in these shapes that the properties of particles are determined. In this vision, the universe is a symphony of strings vibrating in a multi-dimensional space, and time itself is an emergent rhythm of that symphony. Loop quantum gravity takes a different path. Instead of adding new entities like strings, it focuses directly on space-time itself. In Einstein's relativity, space-time is a smooth fabric. Loop quantum gravity suggests that this smoothness is an illusion, that at the Planck scale, space-time is made of discrete chunks, woven together in a network of loops. These loops form a spin network, a kind of quantum lattice, and the geometry of space-time arises from the connections between them. Just as matter is quantized into atoms, space-time in this view is quantized into indivisible units. This has profound consequences for time. In a world made of loops, there is no continuous flow at the deepest level. Instead, time emerges from the transitions between quantum states of the network. The familiar continuity of moments is not fundamental, but constructed, much as a film appears continuous when its frames flicker quickly enough. Time, in this sense, is granular. At scales larger than the Planck time, it appears smooth. At the Planck scale, it dissolves into discrete jumps. Both string theory and loop quantum gravity attempt to address the shredding of time we encounter in black holes and the Big Bang. Strings prevent singularities by smearing them out. Loops prevent infinities by imposing a smallest possible volume and duration. Each offers a way to extend physics beyond the breakdown point. And while they differ in their mechanisms, both point toward the same idea, that time is not absolute, not continuous, and not necessarily fundamental. It is something that emerges from deeper, more primitive structures. Beyond these two leading candidates, there are many other approaches. Causal dynamical triangulations, for example, tries to build space-time from simple geometric building blocks, piecing together tiny simplices in a way that creates a larger fabric. Emergent time theories suggest that time may not exist at all in the deepest equations, that it appears only when we look at the universe from the right perspective. In some versions of quantum cosmology, the fundamental equations are timeless. The wave function of the universe does not evolve, it simply exists. Time, in this picture, is a way of describing correlations between parts of the universe, not a universal flow. All of these attempts reflect the same intuition, that our ordinary understanding of time as something that ticks evenly from past to future is not the whole story. At the Planck scale, time may be woven from vibrations, loops, networks, or correlations. It may be granular, emergent, or even illusory. The search for a deeper theory is not only about solving equations, but about reimagining what it means for time to exist. One of the challenges of these theories is that they are extraordinarily difficult to test. The Planck scale is so far beyond our experimental reach that direct evidence is impossible. Instead, physicists look for indirect hints. Could gravitational waves carry imprints of loop quantum geometry? Could cosmic microwave background radiation reveal traces of string vibrations from the early universe? Could black hole evaporation encode patterns predicted by one theory or another? Each possibility is tantalizing, but so far the evidence is inconclusive. This has led some critics to argue that these theories are more like philosophy than physics. Yet history shows that bold ideas, even when untestable at first, can eventually lead to breakthroughs. The beauty of strings and loops is that they take us seriously when we ask what lies beneath the Planck curtain. They do not shrug and say the question is meaningless. They attempt to give structure to the unknowable, to replace infinities with patterns. Whether those patterns are vibrating strings in hidden dimensions or networks of loops woven into space-time, they are ways of making sense of the smallest scales, ways of imagining what time itself might look like when stripped to its roots. And in both visions, there is a sense of music. In string theory, the music is literal, tiny strings vibrating at frequencies that generate particles and forces. In loop quantum gravity, the music is structural, loops connecting and recombining in harmonies that form space-time. In both, the flow of time is like rhythm, emerging from the deeper beat of the universe. What we call seconds and minutes are the macroscopic echoes of that hidden rhythm stretched out into the scale of human life. These theories also open the door to further speculation. If strings are real, then perhaps our universe is one of many, each with its own vibrational symphony, each with its own time. If loops are real, then perhaps the universe bounces eternally, each cycle separated by Planck-scale transitions where time is shredded and reborn. If time is emergent, then perhaps in some ultimate sense, the universe is timeless, and what we experience as flow is a projection of deeper correlations. These are not idle fantasies. They are serious attempts to grapple with the hardest questions physics can ask. In thinking about these ideas, it is easy to feel distant from them. Strings vibrating at unimaginable scales, loops weaving a quantum lattice of space-time. They seem abstract, remote. But it is worth remembering that they are attempts to describe the very stage upon which we live our lives. The flow of time we feel, the rhythm of days and nights, the arc of memory and anticipation, may all be surface effects of these hidden structures. To contemplate them is not only to ponder physics, but to ask what it means to exist in time at all. And so, as we move beyond the limits of measurement, beyond the shredding of time in black holes, beyond the singularity of the Big Bang, we find ourselves in a realm of theory where imagination and mathematics strive together. Strings, loops, vibrations, networks. Each offers a vision of what might underlie the flow we take for granted. None is yet proven. All are works in progress. But together they point to a truth. That time may not be the ultimate foundation, but a melody played upon deeper strings, a pattern woven into deeper loops, a rhythm emerging from the hidden architecture of reality. When Max Planck first wrote down the constants of nature at the dawn of the 20th century, he could not have known that his name would become synonymous with the smallest units of space and time that physics can describe. He was not setting out to redefine the limits of reality. He was looking for natural units, ways of measuring that did not depend on arbitrary human choices like the length of a meter rod or the swing of a pendulum. By combining three fundamental constants, the speed of light, Newton's gravitational constant, and his own Planck's constant from quantum mechanics, he found a system of units that seemed to belong to nature itself. Among them was the Planck time, the square root of the product of Planck's constant and the gravitational constant, divided by the speed of light to the fifth power. The result was an almost unimaginably small number, about 10 to the 43 seconds. What does such a number mean? One possibility is that it represents something real, the shortest possible tick of the cosmic clock, the indivisible grain of time beyond which no subdivision is meaningful. Another possibility is that it is only a mathematical curiosity, a limit with no physical substance, a scale that appears in equations but has no direct correspondence in the structure of the universe. This question has haunted physicists ever since. The argument for Planck time being real begins with the fact that it arises from constants that govern the most fundamental laws we know. The speed of light is not just a number, but the ultimate speed limit of the universe, woven into relativity itself. The gravitational constant determines the strength of gravity, shaping stars, planets, and the cosmos. Planck's constant governs the quantum, dictating the uncertainty and discreteness of the microscopic world. When these three constants are combined, they yield a unit of time that has no human arbitrariness about it. In this sense, Planck time is not a trick, but a natural boundary written into the equations of the universe. It is where quantum mechanics and gravity meet, where our theories converge and collapse. But there is also a counter-argument. Just because we can combine constants to form a quantity does not mean that quantity corresponds to a physical reality. There are countless ways to combine constants that produce scales with no direct significance. The fact that Planck time is tiny does not automatically make it a true grain of time. It could be that nature is continuous, that time can be divided endlessly, and that Planck time is merely the scale at which our current theories fail. In that view, it is a marker of ignorance, not of reality. The history of physics gives us examples of both. Some natural units have turned out to be deeply meaningful. The speed of light, for instance, is not just a number, but a real boundary. Nothing can outrun it. The quantum of action represented by Planck's constant is not just a curiosity, but the foundation of quantum mechanics, forcing energy into discrete levels. On the other hand, some combinations of constants, though mathematically valid, have no special role in the physical world. The challenge is to decide which side Planck time falls on. One way to probe this is to ask whether there are physical processes that naturally point to Planck time as a limit. Black holes suggest there are. As we saw, trying to probe smaller and smaller intervals of time requires more and more energy. At the Planck scale, the energy density would collapse into a black hole, cutting off further measurement. This is not just a matter of technology, but of principle. It suggests that Planck time is more than a number. It is the frontier where space-time itself resists further subdivision. Quantum gravity theories also give weight to the idea. In loop quantum gravity, the quantization of space-time produces a minimum unit of area and volume, and by extension a minimum interval of time. In string theory, the extended nature of strings prevents physics from probing scales smaller than their length, which is of the order of the Planck scale. Both theories, though very different, point toward the same conclusion. Planck time is not an artifact, but a genuine limit. It is not that the universe stops ticking at that scale, but that ticking itself ceases to be defined. And yet, caution is necessary. None of these theories has been confirmed experimentally. We cannot measure directly at the Planck scale. All our arguments are extrapolations, guided by mathematics and theory but untested by observation. It is possible that the universe has surprises in store. Perhaps time is continuous after all, and the Planck scale is simply where our equations become blind. Perhaps deeper theories will show that the constants combine differently, yielding new scales with new meanings. The humility of science is that we cannot yet know. This uncertainty opens the door to philosophical reflection. What does it mean for time to be real? We experience time as a flow, as a succession of moments. But physics describes it as a dimension, a coordinate like space, structured by equations. If time is continuous in our experience but discrete in reality, which is more fundamental? If Planck time is real, then our experience of continuity is an illusion, much like the illusion of a smooth image on a screen that is actually made of pixels. If Planck time is a trick, then perhaps our experience is closer to reality than the equations suggest, and time really does flow without interruption. There is also the possibility that the distinction between real and trick is not well posed. Planck time might be both, a mathematical scale that marks the breakdown of our theories, and at the same time a physical limit that tells us where new structures must appear. In this sense, it is like the horizon on Earth. The horizon is not a physical object you can touch, but it's also not imaginary. It is a real feature of geometry, telling you something true about the surface of the planet. Planck time might be similar, not a grain of time you could isolate, but a real boundary telling you something profound about the structure of space-time. To make sense of this, it is helpful to think about the history of science. Often, limits we thought were artificial turned out to be real. The idea that atoms are indivisible was once speculation, but it turned out to be true in a qualified sense. The idea that there is a maximum speed was once unimaginable, but Einstein showed it was woven into reality. The idea that energy comes in quanta was once a mathematical trick, but it revolutionized physics. Perhaps Planck time is in the same category, an artificial-seeming construct that is actually a doorway into a deeper understanding. Or perhaps it is not. Perhaps time truly is continuous, and Planck time is nothing more than a marker where our math stumbles. If so, it may be less profound than we imagine. But even then, it would not be meaningless. Knowing the limits of our equations is itself knowledge. It tells us where to look for new ideas, where to focus our efforts. Planck time, even if only a mathematical trick, would still be a compass pointing toward the unknown. What makes this question especially poignant is that it touches not only on physics, but on meaning. If time is granular, then the universe is built from moments as real as atoms. If time is continuous, then the flow we experience is unbroken, infinite in its divisibility. Each possibility carries with it a different vision of reality. Neither diminishes the wonder. Both expand it in different directions. The very act of asking the question draws us into reflection about the nature of existence itself. In the end, whether Planck time is real or a trick, it serves as a reminder of the boundary between knowledge and mystery. It reminds us that our theories, as powerful as they are still provisional. It reminds us that the universe contains scales and structures beyond our reach, and it invites us to imagine what it might mean for time to have a grain, a limit, a smallest beat in the rhythm of reality. When we talk about Planck time, the smallest slice of duration the universe allows us to imagine, it can feel so far removed from daily life that it almost seems irrelevant. 10 to the negative 43 seconds is beyond comprehension, so brief that even the fastest processes we can measure are oceans of time compared to it. And yet, there is something strangely moving about the idea that such a scale exists. It forces us to think not only about the outer edges of physics, but about the way we experience time ourselves, in bodies that live, breathe, grow, and age. Somehow, the smallest possible interval and the longest spans of human reflection are connected by the same thread of time. One way to appreciate this is to think about how we measure our own lives. For most of us, time is counted not in Planck units, but in hours, days, and years. We watch the clock, we feel the seasons change, we mark birthdays and anniversaries. But if you pause and think, every one of those larger intervals is built from smaller ones, nested like layers. A year is built from days, a day from hours, an hour from minutes, a minute from seconds, and seconds from even finer slices. And buried deep at the end of that ladder lies the Planck time, the bottom rung that physics tells us we cannot go beneath. That means that, in a way, every life, every story, every memory is constructed from sequences of moments that, however long they feel, rest upon a foundation of something that cannot be divided further. It is as if the narrative of our lives is written on paper whose fibres are Planck moments, invisible but essential. Thinking this way reminds us how layered the experience of time is. Consider memory. When you recall a moment, you don't recall every tick of a second. You recall a feeling, a scene, perhaps a smile or a voice. That moment in your mind may have lasted minutes, but in truth it was built from countless smaller intervals. The physics tells us that there may be a smallest possible interval beneath them all, but your mind bundles them into experiences impressions and feelings. Planck time may never register in consciousness, but it is always there, setting the ground for what consciousness builds upon. There is also the perspective of mortality. Our lives, no matter how long they feel, are finite. We measure them in decades, but those decades are ultimately made of moments. When you stand back, you see the arc of a lifetime. When you lean in, you see the fragments, the single conversations, the quiet mornings, the unexpected laughter. The awareness that physics recognizes a smallest unit of time can heighten this appreciation. It suggests that every instant is indivisible, that life itself is a string of moments that cannot be split apart, only lived. It does not mean that each instant is a Planck time, but it does mean that life is not continuous in the way we imagine. It has texture, it has grain, even if the grain is invisible, and to know that there is such a grain gives weight to the moments we do experience, the minutes and hours that make up the story of who we are. In another sense, Planck time invites us to think about limits. It is a physical reminder that not everything can be divided, not everything can be stretched infinitely. There are boundaries to the universe, and by analogy, there are boundaries in human life as well. We cannot be everywhere, we cannot do everything, we cannot stretch a moment forever. Just as physics places a floor beneath the flow of time, our own lives are bounded by beginnings and endings. The recognition of that boundary does not diminish life, it enriches it, reminding us to notice what lies within the span we do have. There is also a connection to perception. Neuroscience tells us that the brain does not process time continuously, but impulses, integrating information over small intervals. When you hear a note of music, your brain is averaging vibrations across milliseconds. When you see motion, it is blending frames of visual input. In this sense, your perception of time is not smooth, but stitched together, much like the way physics suggests the universe itself might be stitched at the Planck scale. We are, in our own way, already creatures of discrete moments. The smallest possible moment of the cosmos echoes in the way our minds create the flow of now. Think also about creativity and decision-making. Every choice we make, whether small or large, happens in a moment. A single yes or no, a single step forward or backward, can ripple into years of consequence. If Planck time is the foundation of reality, then those choices too are built upon the smallest scales. The tiniest moment can contain the seed of the largest change. In physics, Planck time is where the laws of the universe break down, where new structures may emerge. In life, moments can be where habits break, where transformations begin, where the trajectory of a life shifts. The parallel is imperfect but evocative. Both suggest that the smallest things matter more than they seem. And then there is awe. Simply knowing that there is a number like 10 to the negative 43 seconds, that such a boundary is even conceivable, places our everyday worries in perspective. The stresses of waiting for an email reply, or the impatience of a traffic jam, or the dragging of a long day. All of these are stretched out over intervals unimaginably vast compared to the Planck time. Our entire lives, from birth to death, are longer than a Planck moment in the same way that the age of the universe is longer than a single heartbeat. To sit with that awareness can be strangely calming. It tells us that we live in an abundance of moments, far more than we can count, and that within that abundance lies room for everything we feel, everything we learn, everything we share. There is also humility here. Physics at the Planck scale is beyond our reach, perhaps forever. We cannot measure it, we cannot see it, we can only infer its existence through mathematics. In the same way, there are aspects of our own lives we cannot fully measure, moments that resist being captured. The intensity of love, the depth of grief, the meaning of a memory, these are not quantifiable in seconds or minutes, they are lived as wholes. Just as physics suggests there is a smallest possible unit of time that cannot be subdivided, life reminds us there are experiences that cannot be broken down or explained away. They are indivisible, irreducible, fundamental. If Planck time is real, then the entire universe is structured on an invisible lattice of moments too small to ever touch directly. If Planck time is only a mathematical trick, then it still shows us the power of thought, the way the human mind can imagine beyond what it can measure. Either way, it mirrors something essential in our lives, that beneath the surface of what we see and feel, there is always more, always a foundation that supports the visible world. When you lie awake at night and think about your life, you may not count it in Planck times. You may think in memories, in hopes, in regrets, in wishes, but somewhere deep beneath those reflections lies the fact that the universe itself has a rhythm smaller than anything you can feel, a rhythm that sets the stage for all rhythms above it. Your life unfolds on that stage, every smile and every breath written into the script of time that rests, ultimately, upon the smallest beat physics can imagine. And if there is comfort in that, it may be this, that nothing is wasted. Every moment, no matter how brief, is real. Every glance, every pause, every thought is part of the chain of moments that stretches from the birth of time itself to the life you are living now. Planck time may be beyond your reach, but the moments it makes possible are not. They are here, surrounding you, passing through you, shaping who you are. To notice them, to live them, is to participate in the fabric of the cosmos itself. You've been with me through a journey that stretched from sundials and shadows on stone, all the way down to the Planck time, the tiniest imaginable tick of the cosmic clock. We've wandered through centuries of human curiosity, we've stood at the edge of black holes, we've looked into the earliest instant of the universe itself, and we've reflected on how all of that connects to the way we live our own days. And now, as everything settles into quiet, it feels like the right moment to let those thoughts soften into something slower, something gentler, something you don't need to hold tightly but can simply rest with. It is a strange thing to spend so much time thinking about the shortest time possible. A number so small it almost slips past meaning. 10 to the negative 43 seconds is not something you can experience, not something you can measure or count. And yet, by holding it in mind, you have brushed against the edges of what the universe might truly be made of. Perhaps it is real, perhaps it is only a mathematical doorway, but either way it has guided you tonight into thoughts far larger than your usual hours. And that, in itself, has a certain calming power. Because when you think of it, even the longest day you've ever had, even the year that felt like it would never end, is overflowing with moments beyond counting. Every heartbeat is already an ocean of time when compared to the Planck scale. Every breath, every pause, every flicker of thought contains within it vast expanses of duration compared to that smallest grain. That means you are living not just in seconds and minutes, but in millions and trillions of hidden layers of time. You're rich in moments, far richer than you ever realize. To drift into that thought is to feel the abundance of being alive. You might even find comfort in knowing that your worries, however large they feel right now, are stretched across spans of time that, compared to the foundation of reality, are vast. If a problem lingers for days, those days are already unimaginably long compared to the intervals that build them. That doesn't make problems vanish, but it does put them into perspective. The universe is so generous with time that it gives you more moments than you could ever need, more than you could ever count, and that makes each one a kind of gift, an opening you can step into gently without urgency. And as you sit or lie here, perhaps already feeling heavier, softer, slower, you might notice the way your own sense of time is shifting, the rhythm of your breathing, the weight of your eyelids, the quiet background of your thoughts. All of these are signs that your mind and body are moving into a different kind of time, one that is less about measuring and more about drifting. You're not counting seconds now, you're allowing them to blur. And in that blur, the idea of Planck time, the smallest interval of all, can rest like a hidden foundation. You don't need to hold it sharply in mind. It can just be there, quietly, like a flaw beneath the dream you're about to step onto. Think of how the universe began in that instant we call the Planck era. Time itself was not yet what it is now. It was new, undefined, trembling on the edge of becoming. From that beginning, stars and galaxies and lives like yours emerged. Every story, every thought, every friendship unfolded from that starting point. To know that the entire history of the cosmos rests upon a foundation of moments, that small can make your own life feel part of something enormous, something endlessly connected. And to drift into sleep with that thought is to let yourself feel that you belong to the same fabric, that you're woven into the same time. If your thoughts wander now, that's all right. They can wander the way light bends around a star, the way orbits drift around a black hole, the way sound trails off into silence. You don't need to follow them closely anymore. Just let them come and go. You've spent long enough holding on to ideas, and now you can let them fade. The words can become softer in your mind, like echoes fading in a large, quiet room. You don't need to remember all the details about strings, loops, black holes, or constants of nature. All you need to hold, if anything at all, is the feeling that you have brushed against the edge of time itself, and that you can now let that edge dissolve into calm. Your breathing is steady. The muscles around your eyes are relaxed. The heaviness in your body is familiar, and as each breath flows out, you're giving away the weight of thought, letting it sink down, leaving space for rest. You can imagine time stretching out endlessly in both directions, back to the very beginning and forward to whatever lies ahead. And in that endless stretch, here you are, in this moment, resting. This moment, though brief, is complete. It does not need to be anything other than what it is. And maybe, if you let your mind drift, you can picture those Planck moments stacked one after another, like grains of sand you could never finish counting. They flow beneath you, like a river so fast and fine you cannot see its ripples, only feel its steadiness. That river carries you now, carries you without effort, carries you beyond thinking and into something softer. Each Planck moment slips by, ungraspable, unmeasured, but together they form the current that brings you to sleep. As you settle into that current, there is nothing more you need to do. The world outside can wait. The clocks can keep ticking without you watching them. The universe can continue its vast unfolding. Your only task now is to rest, to let your own time slow, to let your mind release. Whatever questions remain, whether Planck time is real, whether it is fundamental, whether time is continuous or discrete, those questions can stay unanswered for now. They will be waiting in the morning if you want them. Tonight, they can be background whispers, fading into quiet. You have been listening, thinking, imagining for a long while. Now you can let go. You can let your thoughts blur into the rhythm of your breath, into the softness of the pillow, into the stillness around you. You can let yourself drift off, carried by the smallest moment in the universe, carried by the idea that even the tiniest intervals of time are part of the same vast story you belong to. You are safe in that story, and it will hold you as you rest. Thank you for sharing this time with me tonight. If you found these thoughts calming, and if you'd like to drift through more journeys like this, you can always return here again. There will always be more stories to keep you company, more questions to wonder about as you rest. If you'd like to support this space, you can gently tap like or subscribe, but there's no rush. Just knowing you've been here is enough. For now, you don't need to think about anything else. Close your eyes, let your breathing guide you, and let sleep carry you the rest of the way. Good night.